Hello everyone and welcome to Hello everyone and welcome to MV Tutors. I'm Tsolo and we're going to be looking at the recent June exam that you guys have written. Well, some of you. So it's the 2021 June exam and we're starting with question 1. Alright, and then the rest of the questions will follow within the following days. Okay, so this is multiple choice. We're going to go through it, and yeah, if you have any issues with the memo or you misunderstood something, please just put it in the comment section. Otherwise, let's get started. Alright, so it says, a constant net force acts on an object moving in a straight line. I'm already thinking Newton's second law. Which one of the following quantities associated with the object will remain constant during the motion? Okay, like I said, I'm reminded of Newton's second law where it says you have an object moving in a straight line and then a resultant force acts on it, or a net force acts on it. So the acceleration of the object will be in the direction of that force that is acting on it. And the acceleration is directly proportional to the force, but inversely proportional inversely proportional to the mass. So basically, we are then saying, the net force is equal to mass times acceleration. If you increase the force, if you increase the acceleration, if you increase the acceleration, all right, you definitely increase the resultant force or the net force, because acceleration is directly proportional to the net force. Alright, so here then we would pick C, okay, which is acceleration. Alrighty, now 1.2. The weight of an object on the surface of the earth is W. What will be the weight of the object on the surface of another planet of the same mass as that of the earth, but twice the radius of the earth? Okay guys, just a reminder. Remember that weight is equal to mass times gravitational acceleration. And we also know that gravitational acceleration is equal to that gravitational constant, where you have the mass of someone, or the mass of the earth actually, all over r squared. So if we take this whole term and we multiply it with m, we will then have that, okay, let me put it this way, my apologies, let me just shift that up. So we would have it that the weight is equal to the gravitational constant times the mass of the earth, the mass of an object, that object that we're talking about, r squared. So here on earth, this is what the weight is, okay, but on that other planet, so this is earth and this is the other planet, we are told that the mass of the object stays the same. Okay, so mass of the object is the same, and then so the mass of the planet, but we have twice the radius of the earth. Okay, so we have twice the radius, so this whole term is squared. Okay, so I'm just going to put it on the side. G m1 m of the object, then we have 4r squared. Now I want this equation, so I want this equation here to look closely to this one. Okay, so what I'm going to do, I'm going to take the 4 out. If I take the 4 out, it will be 1 over 4. Then I have my G m over r squared. So then it will be a quarter. Okay, so then we would go with the answer of A, a quarter of the weight. Alright, still with me guys? Okay, let's move right along. Now, 1.3. The diagram below shows a cricketer player moving his hands downwards from position 1 to 2 to 3 while catching a ball. Which one of the following statements correctly explains why the cricketer player moves his hands downwards? Okay, guys, to better illustrate or explain this example, imagine you are jumping. Let's say you're doing high jump, okay? As you go over that bar and you jump over it, you're gonna land on not a sponge per se, but a mat that is spongy, right? Okay, so your time of landing will actually be longer than if you would land on the hard surface. Okay, that will be a disaster if you land on a hard surface on your back. Okay, so the time it takes for the landing will be longer on a sponge than it is on a hard surface. Why? We want to reduce the impact of the force. Okay, so the cricketer here, if he catches that ball and he kept his hands still, okay, that ball, the force that ball is coming with is going to be high and it's going to hurt him. It's going to hurt his hands. But when he now lowers his hands, he's trying to increase the time of the contact with the ball, okay? Increasing the time, therefore sort of, we could say converting the energy, kinetic energy to, I don't know, heat energy or something. But basically, he's trying to reduce the impact that the ball is coming with, and that's why he lowers it, okay? So it has to do with timing, and it has to do with the impact of the force, okay? So reading reading the solutions here. A, the impulse on the ball is decreased. Okay, the change in momentum of the ball is increased. The change in momentum of the ball is decreased. The time it takes to change the momentum of the ball is increased. Yes, I would go with D, because you are trying to increase the time the ball is actually caught. Why? Because you want to decrease the impact of that force. Okay, I'm thinking along the lines of, impulse is equal to force. Is it force times delta T? Yes, it is force. I think it's force times delta T. Okay, so you're trying to increase the time, all right, so that the impact on the player's hands, the force actually is reduced because of the increased time. So yeah, an impulse, that it's actually change in momentum. Okay, so the time it takes to change the momentum of the ball is increased. It really is about increasing the time, guys, or else we're talking injuries here. Okay, I just want to make sure that I have the right equation for impulse. Yes, it is. Okay, now let us go to the next page. Okay, let me just increase there. Okay, right. Consider the motion of a small stone thrown vertically upwards until it reaches its maximum height. Okay, so in my mind, I want to draw it out, like what is happening here. So if I have my displacement versus time graph, okay, this thing is thrown vertically upwards. If I'm choosing upwards as positive, so it will do this, okay, and that's the maximum height that it reaches. Okay, now how would the velocity time graph look? Okay, we know that at its maximum height, that's where the velocity is 0. And if we're taking up as positive, then the initial velocity, guys, it's actually its maximum. So the initial velocity, so here at 0, you have your maximum velocity, okay? And then it decreases until it reaches its maximum height. So if you have your velocity time graph and your displacement time graph, you can actually relate it to these graphs. So momentum, guys, momentum is directly proportional to velocity. So velocity is moving this way, guaranteed momentum is also having the same relationship, because remember, momentum is mass times, okay, it's mass times velocity. Okay, so initially the velocity was high, the mass is constant, so the velocity was high, and then the velocity became 0. So I'm expecting the momentum time graph to actually look exactly the same way. So even momentum, it has the same shape. Now, the same with your displacement time graph, it mimics the potential energy. Yes, I haven't even finished reading the question, sorry. It says ignore the effects of friction. Okay, which one of the following combinations of graphs correctly shows how the momentum and the gravitational potential energy of the stone change with time? Okay, so you have momentum there, momentum, which is mass times velocity, and you have the gravitational potential energy, which is mass times gravity times the height. Okay, so yeah, your displacement time graph, it actually mimics your gravitational potential energy. Okay, so as well, the height was 0 to begin with, and then it reaches its maximum there. Okay, and it's a curved graph. Okay, so which one actually of all these options that we have here, which one tells us exactly what's going on? So I'm just going to reduce this so that we can see all the graphs at the same time. Well, this one, momentum, nope. This momentum, yes. And we also have this one, so great. But the gravitational potential energy, yes and yes. So we can see that our answer is actually D. Okay, cool. Let me change the color of my pen and let's go to the next question. 1.5. Okay, let's just increase the size and just center it a bit, or rather move it to the left. So it says a boy and a girl having different masses are initially at rest at point P. They slide down different paths of a water slide as shown in the diagram below. Ignore the effects of friction. Okay guys, that was very important for them to remind us that we should ignore the effects of friction. Okay, why am I saying that? Because that will actually tell you, do you have a non-conservative force or a conservative force? Okay, so let's just read the statements below and then we'll answer the question. So it says, consider the statements below regarding the boy and the girl. Only conservative forces act on both the boy and the girl while they are sliding downwards. The boy and the girl each have the same gravitational potential energy at point P. On reaching point Q, the speed of the girl is equal to that of the boy. Which one is true? So, if we were not to ignore the effects of friction, guys, remember friction is a non-conservative force, okay, which is path dependent, okay, it is quite path dependent, but we are told to ignore the effects of friction. So air friction on the slide itself, any kind of friction, you're ignoring it. And if you're ignoring it, the only thing or the only force acting on these two individuals, this boy and girl, is gravity. All right, gravitational force, and gravitational force falls under conservative forces. So yes, only conservative forces act on the boy and the girl while they are sliding downwards. Now the second statement, the boy and the girl each have the same gravitational potential energy at point P. Is it true? Remember, gravitational potential energy, which is just U, I like saying EP, but it's fine, U is mgh. It depends on the masses, guys. They told us they have different masses. They even put it in bold. They have different masses. So their gravitational potential energy is definitely different. Okay, even their kinetic energy. Remember here, the potential energy is the highest and their kinetic energy is the highest. Even the kinetic energy is different because I think that's K. So you have half mv squared. Again, it's dependent on the mass. So definitely it wouldn't work out. Okay, so the second statement is unfortunately false. So no, can't be option 2. Now on reaching point Q, remember only gravity is acting on them, okay, because we're told to ignore friction. Now it says on reaching point Q, the speed of the girl is equal to that of the boy. When I first read this, I was like, the speeds cannot be the same because they have different masses. But guys, if you were to be at the top of a building, okay, so you're at the top of a building and you throw a feather and you throw one of those, if you go bowling, those bowling balls. If you throw them, ignoring the effects of friction, both of them are going to reach the ground at the same time, meaning they have the same speed. Yes, that is true. Okay, so remember, a feather has a less surface area, meaning less force acting on it. Okay, and the ball has a bigger surface area, has a bigger weight or rather mass, and a bigger force is acting on it. But ultimately, the gravitational acceleration on both of them will be 9,8. So they will reach the ground at the same time and will have the same speed. So the same with this concept here. We are ignoring the effects of friction. So both of them will have the same speed at Q. Okay, so yes, this one, we are definitely going with it. So we have option 1 and 3. And if we look here, 1 and 3 only, so that is B. Okay, so that was 1.5. Now let's go to 1.6. Okay, so now an astronomer an astronomer observes that the light spectrum of a star has been blue shifted. So you know the color is blue. Okay, how have the observed frequency of light from the star and the distance between the star and the earth changed? Okay guys, the color blue, okay, if we talk about the color blue, it has shorter, smaller wavelengths. Okay, so its wavelength, it's quite small, short. Yeah, short. Let's just stick with short. And if it's short, it means that it has a higher frequency. Okay, and that's different to red. Okay, and that would explain why the sky is blue during the day and then sunset is red. It has to do with this. So red has higher wave, or rather longer wavelengths and lower frequency. But we've been asked about blue. So we're definitely going for shorter wavelengths and higher frequency. So the frequency increased, yes. And the distance between the star and the earth, remember, it's decreased. Okay, yeah, so our option would be B. Okay, and then 1.7, a small negative point charge Q is situated halfway between two identical spheres P and Q carrying identical charges as shown below. So this one here, Q, it's negative. I'm assuming P and Q are positive, but anyway, let's just see. Sphere P exerts an electrostatic force of magnitude F on sphere Q. What is the magnitude of the net electrostatic force experienced by the point charge? So the net electrostatic force experienced by, so F net on Q, that'll be equal to the electrostatic force for P on Q, and we're gonna also add the electrostatic force of Q, big Q over small q. Okay, and remember, this P will be attracted in this direction and Q will be attracted in that direction. we've been told that both have the same magnitude. Okay, and this is exactly halfway. Okay guys, the actual equation, okay, it's K, so you'll have Q for P on Q, and then Q again. No, what am I doing? Sorry, let me just rewrite that. So this is the equation K Q1 Q2 over R squared. Okay, so Q1, if you're looking at PQ, this would be P, and that would be small q. Okay, then we're gonna add again on this side K Q Q and Q small q R squared, and this one would actually be negative. Okay, and that one would be positive, and they have the same quantities, so I mean positive plus negative, you'll end up with a force of 0. Okay, so A would be the answer. Alrighty, I hope that was clear. 1,8. Okay, let us see. So now 1.8. Consider the statements below regarding AC power and DC power. So this is more of your theory that you need to read through. So now AC voltage can be changed during AC power transmission. Yes, that is actually true. DC power transmission requires transformers. No, that is false. It's actually AC power transmission that requires transformers. Okay, and then AC power transmission is more energy efficient. Yes, it is. So our answers, it's only 1 and 3. Okay, so it's C. All right, and then 1.9. In the electric or in the circuit diagram below, all resistors are identical. Okay, we can see R. Ignore the internal resistance of the cell, so that would be right about there, and the resistance of the connecting wires. Okay, when switch S is closed, the reading on the voltmeter V1 is 3. What will be the reading on voltmeter V2? Okay, so you have current, okay, moving along. Okay, this would be the total current, right? And then this current, it splits. Okay, so it splits in this direction, and then it splits in that direction. Okay, here we already know that that voltmeter reading is 3 volts. Okay, so the current there would, okay, let me just write the equation as we first know it. So V is equal to IR, therefore I would be V over R, and we know that V is 3. Okay, so we already know the current here, but we don't know the current there. Okay, so firstly, what I would do, there are a lot of resistors here. I want to get one resistor. Okay, so these two are in parallel, and what do we do when we calculate resistors in parallel? We say 1 over R. So 1 over R plus 1 over R, that's actually 2 over R. But the resistance now in parallel are actually half R. So this condenses to one, it condenses then to one resistance, or one resistor. Condenses to one resistor that is in series with that one. Okay, so here we have half R and we have R. And now resistors that are in series, okay, that would be that half R plus R. So that's actually 1.5 R. So if I condense the entire thing, so if I were to sketch this on the side, what do I have left? Okay, that's my battery. I have okay, I have this voltmeter here, okay? And no, actually I shouldn't put it that way. Let me attempt this again. Okay, so I have my 1 resistor now. I've combined all those resistors into 1, okay, because it's easier to work with 1. Okay, and then so this is my resistor R, and that's my resistor 1,5 R, and around it I have my voltmeter there, so that's V1, and on top of this one I have my voltmeter it'll actually be over the whole thing, but yeah, V2. Yeah, so I have V1 over there and V2. And then when you read your laws, guys, it actually says that voltmeters that are in parallel are actually equal. The reason why I've condensed all these resistors into 1 is because I wanted this voltmeter to be parallel to that one. Okay, so V1 was 3 volts, V2 is also 3 volts. Okay, so meaning the current then going through here, the current that goes this side, we already know the current going through here. The current going through here is 3 over R. Okay, but the current that goes through here, okay, that'll be 3 over 1,5 R, which is 2 over R. Okay, and this current, guys, so we have these 2 resistors in parallel, okay, the half R and the full R. Sorry, they are in series, they're not in parallel. Both of them are in series. The same current will move through here as well as there. So this 2 over R current moves through this, and it also moves through those resistors there. Okay, let me just erase. It's a mess. But yes, we found the current actually going through there. Okay, which makes our life quite easy in answering this question. Okay, so now we are focused here because we want to know what the voltage is on V2. So we know V is equal to I times R. We have found our our I okay, our current, which is 2 over R, and we know our resistance is just R. Okay, and then our answer then will end up being 2 volts. So C is the answer. Okay, and then yeah, we're at the end. Okay, let me just increase the size. Now it says some of the energy levels of an atom are represented in the diagram below. EO represents the ground state energy. Which one of the energy transitions below represents the absorption of light of the lowest frequency by the atom? Okay, so if you know the equation, we have this equation called, I hope I recall, E is equal to Planck's constant is hf. Okay, so from this we can deduce that E is actually directly proportional to f being the frequency, h being Planck's constant. It's a constant that's given in your formula sheet. So if you increase the energy, your frequency will increase. Okay, so now I'm just going to make up values here. So let's say from E1 to 0, E0, we actually have 4 units. Okay, and here, let's say we have 2 units. They will say we have 1.5, and they will have 1. Okay, I'm assigning units because I want us to work out what's actually happening in all of these. So if I go from E0 all the way to E4, I want to know the difference between, I want to know what the actual units are. Okay, so I'm going to add 4 plus 2, which is 6, plus 1.5, which is 7.5, plus 1, which is 8. So I have an energy of 8 units. So from E1 to 3, okay, I have 2 over here and 1.5, so that will be 3.5. Okay, from E3 to E4, that's just 1 unit. And from E0 to E3, that's just 4 plus 2 plus 1.5, and that is so 7.5. I think the first one should be 8.5, not 8. Okay, 4 plus 2, 6, plus 1.5, 7.5, 8.5, yes. So now they're asking which one of the energy transitions below represent the absorption of light of the lowest frequency. Remember, if you have a lower frequency, the lowest frequency, then it means you have the lowest energy level. And the lowest here that I can see is actually from E3 to E4. Okay, there you have an energy with a unit of 1, and that's the least, that's the lowest. So if that's the lowest, it means the frequency there is the lowest. Okay, and yeah, that is it for question 1, guys. I hope you enjoyed it as much as I did. Again, if you have any questions, do please comment below. If there are any uncertainties, if I've said something that is a fatal error, please do correct a person. I don't know everything. I try and I'm open to correction. So yeah, that's it, and goodbye from me. If you'd like to visit our website, please do go to www.mvtutors.co.za. We have content there. You can even book a lesson. If not, you can chat to us on 076 312 1107. Okay, enjoy the rest of your day. Hello everyone, and welcome to MV Tutors. I'm Tolo. We're still looking at the Physics Paper 1 2021 June exam, and let's see what question 2 has in store for us. Alright, so an 8 kg block on a rough horizontal surface is connected to a 2 kg block by a light inextensible string passing over a frictionless pulley as shown below. Okay, so one thing I am noting there is rough horizontal surface, so I know already there's friction. Yeah, okay, and we have a frictionless pulley, so you don't have to consider friction at the pulley section. Okay, the 8 kg block moves at a constant speed. They've put it there in bold, so you know if there's constant speed, there is no acceleration. So the 8 kg block moves at a constant speed when pulled by a 29.6 Newton horizontal force to the right. So there is a force applied. So this whole system is going to move to the right. Okay. Yeah, let me just remove all of that. But yes, we know that it's moving to the right. Okay. And that's cool. The frictional force acting on the 8 kg block is 10 newtons. So they've given us the value of the friction force. If they had given us the coefficient of friction, then we would have had to calculate it ourselves. But our job is light. All right, so now 2.1, state Newton's second law of motion in words. Okay, so when I think about Newton's second law, I think about me driving on a straight path and I'm moving at constant velocity, and then out of the blue somebody just bumps me, and then my car ends up moving in the direction of that person who bumped me. Okay, so if a body is moving at constant velocity, if a resultant force acts on that body, the body will move in the direction, or will accelerate at the direction of that force. So that's just Newton's second law summarized. Basically, you require a resultant force, and that body will move in the direction of the force, or will accelerate at the direction of that force. And that acceleration, my dear friends, is directly proportional to force and inversely proportional to mass. And when you think about the mass, think about inertia. What is inertia? Inertia is the body's resistance to movement. So if I'm moving at a certain velocity and some external force comes, I try by all means to resist that external force. Okay, and the heavier something is, the higher its inertia, the higher its resistance to the movement. So that is why the acceleration is inversely proportional to mass, yet it's directly proportional to the force. Okay, so let's write that down in words. That was a nice story, but at the end of the day, you still need to write it down, right? Okay, so 2.1, I'm just going to write it there. Can't see my cursor. Oh, I'm at the wrong place. Okay, now what did I do? Alright, so I'm just going to make it a bit smaller so that I can write on the side. Okay, so 2.1. So the net force net force acting on an object will cause that object to move in its direction. But so the net force acting on an object will cause the object to accelerate in its direction. Accelerate. Ooh. Okay, the net force acting on an object will cause the object to accelerate in its direction. Why does it do that? Okay, and then that acceleration, I'm just going to use symbols now. The acceleration is directly proportional to the force, and it is inversely proportional to the mass. Okay, so firstly state the force is a resultant force. It's acting on an object. It's causing the object to accelerate in its direction. Then you talk about the acceleration. The acceleration is directly proportional to the force and inversely proportional to the mass. Alright, and that is 2 marks. I think it's fair. Okay, so let's zoom in again and see what the next question is. So draw a labeled free body diagram of the 8 kg block. Okay, I'm just going to draw it on the side. I thought maybe it would be better drawing it on the drawing itself, but it might be a bit untidy. Okay, so there is the 8 kg block. The easy ones, we know that we have the normal force, which is perpendicular to the surface. Then we have the force of gravity, gravitational force, that is due to the weight of the object. Then we have the force of tension. That's the string. Let me make it a bit longer. So we have tension force. Then we have the applied force. And guys, this is where you scoop marks. I mean, it's 5 marks. That is a lot. We have the force applied. Actually, this force applied should be longer than the tension force, for the mere fact that the whole system will be moving to the right. So you want to make the arrows sort of relative to the magnitude of the force. So we can see that the force applied, which is actually 29.6, that it is longer, shows that it is much bigger. And then we have friction force. Friction force will definitely be small. So you can just say friction force, or you could say kinetic. You can show FK or big F and small f. It's really up to you. I actually prefer using FK because I'm showing that this is it's moving. If it were static, I would use Fs. So Fk will do. And if you wanted to put the values there, obviously that would be 8 times 9, 8. But they didn't ask for values. They just wanted... Okay, they said draw a labeled free body diagram. So, and it's 5 marks. So you wanna... you wanna make sure you scoop all those marks. So let's just calculate what 8 times 9, 8 is. Okay, 8 times 9, 8. And that is 78,4. So that is 78,4 Newton. Okay, and your friction force, well, they gave it to us, and that was given as 10 Newton. Okay, yeah, so that is it, guys. That's a free body diagram. That's 5 marks, a nice 5 marks if you would ask me. Okay, so now let's go back and read the rest. Okay, now calculate the tension in the string. Okay, let's go and look. So it's 3 marks. So I am moved by the marks here. You could either calculate the tension in the string by looking at the 8 kg block. Okay, you have your force of friction just by looking at our free body diagram. You have the force applied, right? 29,6. You have your force of friction. You can calculate your tension. Fair enough, right? It's actually going to be 29.6 minus 10, which is 19,6. Great. 3 marks. Got it. Or you could use this 2 kg block. Okay? The only forces acting on it is the force of gravity and the force of tension. So yeah, you can calculate it whichever way is easiest or best or quickest for you. Because after all, this is an exam and you don't want to waste time doing things that would take long. So, looking at this free body diagram, remember it is not accelerating. So when you look at the forces, the net force in the x direction, okay, you're going to have your force applied, right? Which is going to the right, which is positive, right? We are choosing right as positive. And then we're going to subtract the force of tension, and we're going to subtract the friction force. Okay, the force applied there is 29,6. The tension force, that's what we're looking for, right? And the force of friction is 10. And remember, guys, according to Newton's second law, right, the net force, it's actually equal to mass times acceleration. And they've told us there is no acceleration because of constant velocity. Hence, this term on the left-hand side will actually be equal to 0. So, you're going to have 0 this side. And then 29 minus 10, that's actually 19. 29.6 minus 10 is 19.6. Okay. And then, ultimately, the tension force will be equal to 19.6. Now, if you were focused on this, the block, the second block that's hanging, okay, you could have used that as well. Let me just use the side. So, yeah, you could have said or. Okay, so looking at that 8 kg block, you have the force of gravity, and then you have the force of tension. And we know it's moving at constant acceleration, so you, again, the net force is equal to the tension force minus the force of gravity. The net force will be 0 because of constant velocity. The tension force is what you're looking for, and force of gravity is 9,8 times 2. 9,8 times 2 is 19,6. Taking the force of tension that side. So again, you get the same answer, 19,6. So you have options. Okay, you're not limited to one way of doing it. Alright, now let us see. What else do we need to answer here? Now they're saying the 29.6 Newton horizontal force is now increased to 50 Newtons. So there we go, that external force being applied, it's applied to the right. Actually, the right. And then everything else, all the blocks are going to also move to the right, right? Right, yes, to the right. Oh gosh, this This webcam is, yeah, so this is actually my left hand, but yeah, it's going to the right. So like we said in Newton's second law, okay, so basically we're going to apply that. So now they're saying applying Newton's second law to each block, calculate the magnitude of the acceleration of the 8 kg block. Okay guys, the acceleration on the 8 kg block is also going to be the acceleration on the 2 kg block. Okay, but yeah, let's get right to it. So 2.4.1, I think I'm going to do it this side. Okay, yeah, 2.4.1. Okay, I am going to look at the 2 kg block now. All right, and or should I look at the 8 kg? Let me start by looking at the 8 kg block. I have my free body diagram there. So again, the net force in the x direction. I don't know why it likes smudging. So the net force in the x direction, it will be equal to the force applied, okay, which is now 50, minus the tension force, which is 19, well, it was 19.6 when 29.6 Newton was applied. Now we don't know what the tension force is now, okay? So don't make the mistake of substituting 19.6. It's not, it has changed. Okay, so we have the force applied minus the tension force minus the friction force. But this time there is an acceleration, okay? The mass is 8 and there is an acceleration. We know our applied force is 50. Our tension force, we don't know. Our force of friction is 10. Okay, so simplifying it, I have 8 times acceleration, 40 minus tension force. I have 2 unknowns, guys, 2 unknowns. I need another equation. Okay, if there are 2 unknowns, then there are 2 equations that we need to look at. Okay, so on the other side, looking at the 2 kg block, I still have only tension and the force of gravity acting on it. So again, I'm just gonna say this is equation number 1. And then secondly, I have the net force. This time it's acting in the y direction. Okay, then I have the tension force minus the force of gravity. Okay, again, force is mass times acceleration, so the mass is 2, acceleration is just a. The tension force we are looking for, and then it's going to be 2 times, well, the force of gravity is 2 times 9,8, which is 19,6. Okay, so now I have 2 equations, 2 unknowns. I'm just going to write this equation in terms of Ft, tension force. So then I have 2a plus 19,6. Okay, and this is my second equation. Okay, so we're going to solve simultaneously. So, oh, look at me, I erased I erased my values there unintentionally. So 19,6, 19,6. all right, so now I'm going to substitute equation 2 into equation 1. all right, so yeah, equation 1, I have 8a is equal to 40 minus Ft. And what is Ft? Ft is actually 2a plus 19.6. all right, so I'm just gonna remove the brackets. So I have 40 minus 2a minus 19,6. okay, taking 2a that side, then I have 6 times, oh no, it's negative 2a. It's coming that side, so that's going to be plus, so this will be 10a. And then 40 minus 19,6, yeah, okay, that's probably going to be 21,4. Alrighty, I'll check with the calculator now. Yeah, no, it won't be 21, it'll be 20. It has to be 20. Yes, 20,4. Ne? Because if I take that 0.4, that side is going to be 20. Yeah, it has to be 20,4. And then the acceleration, guys, ultimately we're going to say 20,4 divide by 10. And then the comma is just going to move to the right, to the left actually. So I have 2,04 meters per second, and that is my acceleration. Okay, like I said, the acceleration of the 8 kg block is the same acceleration as the 2 kg block, so we're good. Alrighty, now what do they want? Now they want the tension in the string. So this is now the new tension. Okay, so it's all good. I do have an equation in terms of tension, so yeah, that was good of me to actually put it in terms of tension force and I don't have to do much work. So the tension force is equal to 2 times the acceleration plus 19,6. The acceleration, as we have calculated, is 2,04 plus 19,6. Okay, I'm just going to put this in the calculator. I'm not going to try to calculate it in my head lest I make silly errors. It's nice to have the confidence of calculating in your head, but sometimes you have so many things going on in your mind. You're thinking about the next question, you are stressed in an exam room. So I mean, even saying 1 plus 1, you could just put a 11 there instead of a 2. So it's always safe using the calculator. Alright, so yes, we have 23,68, and that's the force of tension. 23,68. And yeah, that's it, guys. We are done with question 2. That was actually nice. Not so bad. I think if you were to struggle with this, it would be making silly errors, forgetting your new 10-second law and how to apply it, and forgetting that when you have constant speed, actually there's no acceleration, you know. So just be wary of those tiny issues, but other than that, it's all good, guys. 17 marks, bagged it, good. Next question. Okay, hi everyone. So yeah, I'll be doing question 3 with you guys, and let's get right to it. Alright, it says a ball of mass 0,06 kilograms is thrown vertically upwards. So by them saying it is thrown, we know that there is an initial velocity. Okay, it's not dropped, it's thrown. So it's thrown vertically upwards, as you can see here, from the balcony of a building, okay, 3 meters above the ground. The ball reaches a maximum height, and that's the h there, above the ground, as shown in the diagram below. Ignore the effects of air resistance. Okay, so let us get to the questions. Alright, I'm just gonna, it's fine. As long as you can see the question. So 3.1, name the force acting on the ball while it is in free fall. Okay guys, it's 1 mark. It's an easy question. You know that in free fall, the only force acting on a body, on an object, on a ball, it'll be gravitational force. Okay, it's the force of gravity. Alright, so I'm just gonna say gravitational force, because it's acting downwards. So gravitational force, I'm just gonna put an F there, gravitational F. Alright, and on to the next question. So now we have a velocity time graph, okay, and it represents the motion of the ball from the instant it is thrown upwards until it hits the ground. Okay guys, if you're given a velocity time graph, here's one thing you should know. The area, okay, like here you've seen area 1, it tells you about the displacement. So if you wanted to know the displacement, or rather how, let's say for this portion over here, if you wanted to know how high this is, okay, you would use the area under the graph, and the area under the graph would be half, okay, and then it will be delta t times the velocity there. Okay, so this velocity here, which is your height, half base times height, right? So your velocity would be your height, and your time here, delta t, would be your base. So half base times height, that will give you the displacement. Okay, so if we had the value of the initial velocity, I would tell you how high this is. Okay, so that's one thing you should know. And then this area over here, well, basically it gives you the whole displacement here. Okay, and you can see it's much bigger than the first one there, so that would be delta h actually. So y here, that is h, not delta h, just h. Okay, so what are they saying now? It says write down the acceleration of the ball at time 1,0 seconds, or 0.2 seconds. So the acceleration, guys, 1,02 seconds, that is when it has reached its maximum height. At that point, velocity is 0. Okay, so the only acceleration acting, which is constant, that would be gravitational acceleration, and the value of that, wow, they gave you 2 marks. The value of that would be 9,8 meters per second squared. Maybe it's 1 mark for the value and 1 mark for the unit. Okay, now they're saying consider the areas A1 and A2 shown in the graph above. Write down the numerical value represented by the difference in the areas. Okay, guys, I took some time in explaining that the second graph here, okay, that is actually the whole of h, right? And the first graph here, it just represents this first portion. So if you want the difference between h and that portion, we can see on the graph that it's actually 3. Okay, so our answer then would be 3 meters. Okay, so let us go back. Yeah, so the numerical value, and it's 1 mark because they are not expecting you to be calculating anything. It's something that you really can see. Okay, so that would be 3 meters. Okay, now 3.4.1, calculate the speed at which the ball is thrown upwards, and that is the initial velocity that they are looking for. Okay, guys, so now in this case, you're gonna go to your to the back of your question paper in the exam, and you are going to look for the equations of motion. You're going to decide which one is actually the best to use here. So I'm just going to write a few of them. Okay, so I've written them down for myself because I don't know them off by heart. And I mean, they're provided in the question paper, so you don't need to cram them. Okay, so the first thing you would have, if you have the final velocity, you know, and the initial velocity, then you would say plus, what is it, acceleration delta t. Okay, now the signs, so you need to be careful here. Are you choosing up as positive or down as positive? I normally like choosing down as positive because I know gravitational acceleration is always acting down, but in this case I'll choose up as positive. So if we are choosing up as positive, and we know that gravitational acceleration is actually acting on this ball, then this equation then becomes, okay, we have final velocity is equal to initial velocity minus, because if I'm choosing up as positive, then it means down is going to be negative, right? So it will be negative g delta t. Okay, is it an equation we can use? We are looking for the initial velocity. We know our final velocity is 0. We have a gravitational acceleration, and we have time, so we can use this equation. Okay, so yeah, there are many others. We'll use them as we go. I'm not going to write all of them now. I thought I will, but you have them with you, so it's fine. We can go ahead. So now we know our final velocity is actually 0. Okay, our initial velocity is what we are looking for, and we know that g is 9,8, and we know that the time taken to reach the highest point is actually 1,02 seconds. Okay, now, okay, what did I want to say? yeah, we're choosing initial velocity is being taken up, so yeah, this will be a positive. Okay, so now if I take initial velocity that side, it's going to be negative, and we're left with negative 9.8 times 1,02. Okay, then finally our initial velocity we can calculate using the calculator. Okay, where are my calculators? There. All right, so we have 9,8 multiplied by 1,02. Ooh, no, 02. 1,02, and that is equal to 9,996. We normally round up to 2 decimal places, and if you do, you realize that it's actually 10. Okay, so our answer is 10 meters per second. Okay, cool. Now they want height h. Okay, we go back to our equations of motion. Yeah, I'll calculate it 2 ways. Okay, so we go back to our equations of motion. I'm just going to browse through mine and have a look which one to go with. So we have one. Sometimes it's delta x, but because we're looking for a vertical distance, I'm going to go with delta y. And that is equal to the initial velocity times delta t minus because we've chosen gravity as going down, and our positive is actually going up, so minus half g delta t squared. Okay, now we know that our initial velocity is 10. We just calculated it. We know that it reaches its maximum there at time 1,02. Okay, we have 9,8 there, again 1,02 squared. Okay, so we can plug all of that in the calculator and we'll see what we get. Okay, so what we are calculating right now, let me just make sure we're on the same page. What we are calculating right now is this value here. Okay, they want the full h, so after getting this answer we're going to add 3 to it. Okay, so that we can get the full h. Okay, so we're going to plug this in the calculator, and yeah, so yeah, I'm going to use 10 times 1,02 minus 0,5 times 9,8 times 1,02 squared. Okay, and that's 5,1. Rounding off to 2 decimal places, it's just 5,10. You can write 5,102, but I'm just going to stick to 5,1. Okay. Alrighty, so answer is 5,1 meters. Alright, and like I said, guys, the final h is when you add 3 meters to it. So 3 plus 5,1 meters, it's also meters, and that's going to be equal to 8,1. We don't need the calculator for that. 8,1 meters. Another way of doing it, I'm going to just show you quick. Remember this graph? And I told you to get y, you're going to say half delta t times v. So if we did that, it's going to be half delta t is 1,02, and v we calculated it to be 10. So if you get that answer, let's just calculate that quickly. So we have half times 1,02 times 10. Okay, and that is 5,1 on the dot. All right, so yeah, you have options, guys. Whichever one is easiest for you, go with it. And that was 4 marks. That was a nice 4 marks. And then finally it says 3.5. So after hitting the ground, the ball bounces vertically upwards and reaches a new maximum height at 1,1 seconds. Okay, so let's just remind ourselves. So what happened? A ball was thrown upwards, then it went all the way down, and then it reaches a maximum height again. So here our velocity was 10 meters per second. There our velocity was 0 because it reached its maximum height, and that was at time 1,02. Then here, okay, at this point, if I zoom in here, okay, actually it's like it's coming down, right? This ball is coming all the way down. Then it is in contact with the floor, quite exaggerated, and then it goes all the way up again. Okay, so this is, yeah, if I zoom this in, okay, so it hits the with the velocity here, and then before it goes all the way up, it hits with another velocity. But they told us here, when it reaches its maximum height here, it is at 1,1 seconds, and we know at a maximum height velocity is 0. So we want to know what is the velocity here and the velocity there, because we know here the velocity is 0. Okay, yeah, but anyway, we haven't even read the question. So it says calculate the work done by the ground on the ball while the ball is in contact with the ground. So it's in the air here, then through free fall it touches the ground, or it's in contact with the ground. Okay, so now they want the work done by the ground on the ball. Okay, so here it's potential energy, right? But once it reaches the ground, you have kinetic energy. Okay, so if you were to use your work equation, okay, for non-conservative forces, you would have delta EK, so the change in kinetic energy plus the change in potential energy. At that point there on top, okay, that's where the potential energy is the highest, and that's where actually kinetic energy is 0. So as it goes down, your potential energy decreases and your kinetic energy increases until it reaches the bottom, where your kinetic energy is actually its maximum and your potential energy is 0. So already know this is 0. Okay, so we're going to work out what our change in kinetic energy is. Hence I need the velocity there and the velocity there, okay, to work it out. So let's see, what are we going to do? We're going to use our equations of motion. Which one is it going to be now? Okay, let's just take this a bit up. Okay, so the one I'm going to go with, let me just write them. So I have, yeah, final velocity, initial velocity minus g delta t. Are we going to use this, or are we going to use that squared plus, oh actually it's minus 2g delta y. Okay, let me just stop for a moment. I'm looking for the velocity at this point here. Okay, so what do I have? I have that my initial velocity is 0. Now I'm looking for my final velocity. Okay, initial velocity is 0, final velocity, that's what I'm looking for. And I don't have the time it takes from the point it was at its maximum to the ground. They didn't give me that, so I can't use this equation. But if I look at that one, I do have the total delta y, which is 8,1. Okay, so I can definitely use this one. Okay, so I'm looking for my final velocity. Okay, so my initial velocity was 0 because I come from the maximum, and I know that's 9,81. Oh, 9,8, sorry, in varsity we use 9,81. And then your delta y, guys, we chose up as positive, right? But if you look at the motion of this ball, it's going down. Okay, so here we must definitely use a negative 8,1, not a positive one. Okay, and then our final velocity, that'll be the square root of, okay, so these negatives will cancel each other. So I will have 2 times 9,8 times 8,1. All right, so let's just shift it a bit this side. I'm gonna call upon the calculator. Okay, and then you're gonna work it out. So we have 2 times 9,8 times 8,1. All right, and then we have 12,6. Nice. It's a nice number, not much to round off. So 12,6 meters per second. Okay guys, let's go back to our sketch. So this 12,6 meters per second, it is here. Okay, now it gets in contact with the ground and then it leaves with a certain velocity. This velocity here, I'm expecting it to be less than 12,6. Why? Because when it's in contact with the ground, it loses some of its kinetic energy to sound. You know, when you have a ball bouncing, there's a sound produced, there's heat produced there, so you will have a lesser velocity because you have a transfer of energy. So you have from kinetic energy to sound energy to heat energy. Okay, so, but yeah, let's calculate it. And how are we going to do that? Well, basically, okay, I've lost my cursor. Oh, there it is. So basically, we know when it reaches its highest point there, the velocity is 0. And they've given us the time. They said it's 1,1 seconds, right? Yeah, 1,1 seconds. So what are we going to use? We have our final velocity. There, it's 0. We're looking for our initial velocity. And we've been given time, so I'm definitely going to use this equation. Okay, so that was the first part. Then the second part, using this equation. Okay, and at this point, it's going up, right? So, our final velocity is 0. Our initial velocity, that's what we're looking for. Okay, and then we have minus 9,8 and our time is 1,1. So then our initial velocity will be 9,8 times 1,1, and let us find out what that value is. Okay, so we have 9,8 times 1,1. And that value is 10,78. Okay, awesome. No need to round off. 10,78 meters per second. It's like I have grid lines there, but I'm not even using them. They're supposed to guide the way I write. But anyway, okay guys, so we have our two velocities, right? 10,78 and we have 12,6. Now they this is when it was in contact with the ground. They want to know the work done by the ground on the ball. Okay, so let us finally calculate work. And we've already established that work is just going to be the change in kinetic energy. Okay, there's no potential energy there at the ground. At that point, potential energy is 0. Alright, so we have half m, and we have final velocity squared minus initial velocity squared. So the weight or the mass of the ball, they said it there, I forgot at the beginning when we thought it was useless information. So the mass of the ball is 0,06 kilogram. Okay. Alright, 0,06 kilogram. We use kilograms here, guys, not grams. And then our final velocity. So looking at our sketch here, our final velocity is 10,78. Initial velocity is 12,6. It helps to sketch, guys. For me, I really understand better when I sketch these things. I can visualize it and I'm like, okay, we're going for this. So sketch for yourself if you're a visual learner, okay? If you can get things in your mind and it's all good, you don't need to visualize it, then great, good for you. But I need to see, what am I working with here? So don't forget the squared and minus the initial, which is 12,6 squared. And then we're going to call upon the calculator again. And let's see, what is the work done? Remember, work done is measured in joules. Okay. So we have 0,5 times 0,06, and in our brackets we have 10,78 squared minus 12,6 squared Yeah. And our answer is negative 1,28. Okay. Negative 1,28. Let me just write that again. Alright, negative 1,28 joules. And why is it negative? This ball is coming in contact with the ground. The kinetic energy this ball is exerting on the ground, it comes as positive. The ground exerting the energy or the force on the ball, it'll be equal and opposite. Okay, so yeah, if it was the ball to the ground, we would have positive 1,28, but because it's the ground to the ball, it's negative. And it's also negative because it shows us that, okay, it's negative because it shows us that you're losing energy. Okay, you came in with your kinetic energy all strong and powerful, and then you lost it to sound. You lost some of it to sound, you lost some of it to heat, and that's why it went from 12,6 meters per second to 10,78. So when you think about these things logically, even when you get your answers, you're like, does this make sense? You know? So yeah, and you can comment below, just say, how are you doing things? How are you calculating things? Has it been working out for you? What tips can you give to your fellow matric students? Or if you have questions, guys, please put it in the comment section. I know I went through this rushing, not even asking if you guys are following. Sorry about that. But yeah, ask questions. If you have, papers you want us to do, please just tell us. We're here to serve you, okay? And if you need a lesson, you can contact us on our website, www.mvtutors.co.za, or you can book a session on WhatsApp, 0763121107, and we'll be happy to assist you, okay?
Well, good morning once again. It's me, Figure. So we're gonna do question 4 now of the 2021 June exam, which you just wrote a few weeks ago. Okay, so here we go. Question number 4. A simple rocket system consists of two parts: A, of mass 3m, what a weird mass, and B, of mass 2m. I wonder what that m stands for. As shown in the diagram below, B is stacked on top of A. Okay, I see it in this diagram over here. Right, okay. Now the first question is, states the principle of conservation of momentum in words. Okay, so this is just theory work. You should just you should know this already, but in the event that you don't know, let me just write it for you. Now, the conservation of momentum says that actually the total momentum looks like I'm gonna need more space here. Let's get more space. How about that? I want to write a long sentence. Okay, so the total momentum of an isolated system remains constant. It remains constant. Well, it's just as simple as that. The total momentum of an isolated system, okay, or closed system, it remains constant. Okay, that means the initial is equals to the final. It's just constant. That's all. Okay, now let's see what the next question says. It says, now the rocket is traveling vertically upwards at a constant speed v when an internal explosion causes A to move downwards at a speed third of v. Okay, so it's demonstrated after here. A moves downwards. Right. Now, ignore all external forces on the rocket. Calculate the velocity of B in terms of V immediately after the internal explosion. Okay. Alright, it looks like we are going to need our principles of conservation of momentum here. We're going to have to apply the impulse. Let's just write that down. I prefer a red pen over a blue. I feel like the red, it pops more. I don't know if you agree, but this is live, so write down on the comment which pen is better, red or blue. Okay, otherwise let me just continue. So we need the impulse momentum. We know that the sum of the impulse initially is equals to the sum of the impulse, or just say momentum final. Okay, and then now we need to write the actual formula. Now if you look here, mass A and mass B are actually together, so I'm gonna put them together as well here. I'm gonna call it mass A plus mass B, and they are sharing a velocity. Remember, if you don't know, momentum is equals to mass times velocity, so they are sharing an initial velocity. Let's call it VI. Okay, and that's gonna be, now what's happening on this second picture right here is that they are now separate, as you can see. So now we are also going to separate them. We're gonna say mass A has its own velocity, okay, which we'll call velocity, actually let's call it velocity A. Okay, because now we need to choose a direction that's going to be positive. Let's just say going up is positive. Okay, now what that does is that, as you can see, the mass A and its velocity, they're actually going down. Okay, so going down is going to be a negative direction, so it's going to be mass, or actually let me just be consistent with what they called these. Let me call it B instead of A. So I'm gonna rub this, okay, because I just want to make sure that I'm consistent with the naming here. I'm actually talking about mass B, okay, and it's a velocity B, and since A is going the opposite direction, it's gonna be mass A times V A. Okay, now we need to take a look at what we have. Did they tell us what mass A was? Let's check that out. So mass A is 3m, mass B is 2. Okay, so let's just fill that in quickly while we're still here. So this is mass A, we said, is 3m, plus mass B is 2m, whatever m stands for, I have no idea. And are we told the velocity? All we know is that they are at a constant velocity v. Okay, they're going together at a constant velocity v. Okay, now I'm just filling in the information that we have, but let's just read. What are they looking for? Calculate the velocity of B. Okay, B is the one going up. That's what we're looking for. Right, so what is the mass of B? Once again, mass of B is 2m, and its velocity B, that's it, minus mass of A is 3m times its velocity A. Now there's something they said about that velocity here, velocity of A. They said it causes A to move downwards at a speed of 1/3 of a v. Okay, so we know that a velocity of A is 1/3 of v, so we're just gonna put that, we're gonna put 1/3 v. Okay, now all we have to do is to do some mathematical gymnastics. I like that. Okay, so we're just gonna combine these. 3 plus 2 is 5. I don't like this m. Let me just remove it for now, for simplicity's sake. So this is 5v is equals to 2vb, which is what we're looking for, minus, well, these 3's will cancel each other. That one will cancel that one, and I'll be left with just v. Okay, and then if I take that v to the other side, I'll be left with 6v is equals to 2vb, and then therefore we can conclude that vb is equals to 6 divided by 2, which is 3. Now I want you to write on the comment section what are the units of v. Okay, and what I'll say, I just want the units from you, but since it's a positive number and velocity is a vector, by the way, velocity is a vector but speed is a scalar. Now, do you know the difference between a vector and a scalar? Let me tell you a little bit. The difference between a vector and a scalar is that a vector has a direction while a scalar does not. So if they ask for speed, you just give the unit on its own, like 3 blah blah. But if they ask for a vector, which is velocity, then you need to give direction as well. So we're going to say, because it's a positive number, it is going upwards. That's it. That's it. But from you, just write down in the comment section and let me know what the units are. I'll come back and fill them up later. You just gotta read your comments first. Okay, right, let's go to the next question. Now they say the graph below shows the average force exerted by A on B during the internal explosion as a function of time. Okay, so we can see it explodes, boom, goes up, and then it's constant, it goes boom, ooh, and then it falls down. All right, as time goes on. This is the average force. Now it says, name the physical quantity represented by the area under the graph. Now this requires you to know some few theories. Okay, you will know that the area under the first graph is actually what we call impulse. Ladies and gentlemen, we're still on that trajectory of momentum. We're still talking about momentum. Okay, so remember what impulse is? Here we go. That's impulse, m times v, which is the combination of this is what we call momentum. All right, but impulse, that's it. The area under this is what we call impulse. Now let's go to 4.4. What does it say? It says, draw the graph in your answer book on the same set of axes. Sketch the graph of the average force that B exerts on A as a function of time. Okay, so if A exerts on B and we get this graph, what's the opposite of that? Remember Newton's laws? Which law is the one that says if body A exerts a force on body B exerts the same but opposite force on body A? What law is that? Do you have an idea? Well, if you do, drop it down on the comment section. But this let's just redraw it real quickly. Okay, so what I'm gonna do is that I'm gonna pick that. No, I do not want a red pen. I want it black and I want it light. There we go. So I'm just gonna put it right there, and then I'll draw another one there, and then I just want to redraw that one that's on top. So it's actually like this, isn't that right? It's like this. It's a box. It's like that. There. Okay, now if the answer is opposite but equal, now that means now the answer, I'll draw it in red. That means it's going to be like this. It's equal but opposite, right? Right? Just like that. Just like that. Equal but opposite graphs. Well, I could have done a better job there. In fact, let me remove this one as well so that it looks a little bit prettier. There we go. You know, I should have, next time I'll just bring a grid paper so it's much more cuter. You know, I can actually do that right now, but in the interest of time, I will not. Ladies and gentlemen, we are done with this question. What's left for you to do is just to actually label this graph. So this is going to be, let's have it thicker. This is going to be time in seconds, okay, and then this is going to be force in newtons. That's it. Thank you so much. I'll see you next time.
All right. Hello there again. So we are going over to question 5. Okay, we're still doing the paper 1, physics, written in June this year. Okay, so let us read what it says. So, a demolition ball is used by a crane to break the wall of a building. It's like a wrecking ball, if y'all remember Miley Cyrus's song. Alright, the demolition ball of mass 1,250 kilogram is lifted by the crane to a point R. Okay, so you can see there's R. Okay, and it's lifted 5.8 meters above, if this is our reference. Okay. And then, yeah, to a point R at a height of 5.8 meters above its lowest position in 60 seconds. Okay, ignore air friction. So, let's see what is happening here. What do they require of us? So now they say, define the term power in words. Okay, so if I were you and I had forgotten what power is, I would go to my formula sheet, and then there I would find that power is actually equal to work done over time, or change in time. And that is that, guys. You can actually say that. So power is the work done per unit time, or you could say the rate at which work is done. Okay, that would also work. The rate at which work is done. As soon as you see the word rate, then you know that time is involved. So I like that definition better. So power is the rate at which work is done. Okay, rate at which work is done. Okay, now 5.2, let's just put it up. Calculate the average power dissipated by the crane in lifting the demolition ball to point R. Okay, so average power, you would know that, let me just actually reduce this a bit and write the answers on the right. Okay, let's make it a bit neater. So 5.2, the average power, if you were to look at your formula sheet again, so you would know that average power is actually, it's actually average force, the handwriting there, times the velocity. Okay, so in this case, we are not given velocity, we're given time. Okay, but we can actually make a plan. So, you would know, looking at this formula here, when we used to define power, it's work over time. Okay, so I would rather go with that definition. Okay, work over time, but also remember that force, okay, remember that work is equal to force times displacement. Okay, so using this equation, work over time, I would actually use this. So average power, I would use the average force, okay, times distance. Okay, let me just take this a bit up, or over time. And why can I say that? Remember velocity, ne? Velocity is actually distance over time. Okay, or displacement over time. So we've substituted this velocity here with displacement over time. Okay, alrighty. So now, what then is this average force? If you look at the ball there, guys, when it's up in the air like that, the only force acting on it is actually gravity. Okay, so we're actually looking at gravitational force. Let me put it this way. So we're looking at gravitational force, and gravitational force is equal to mass times the gravitational acceleration. Okay, and then the distance. Okay, so there we have your 5.8, because that's a distance above that reference point there. Okay, above its initial position. Okay, so and then the time, we also have it there. I think they said in 60 seconds. Let's check on the question. Yes, it is 60 seconds. Okay, so we do have everything that we need to calculate, to calculate what the power is. Okay, and there we go. So the force of gravity, it's actually 1250 kilograms times the 9.8 times the 5.8, that's the distance. Okay, and time 60 seconds. And remember, the unit of power is watts. Okay, so we're just going to get the calculator and calculate that. Okay, let's just do that. So get 1250 times 9.8 times 5.8 all over 60. Okay, and our answer is 1184,17. Okay, so 1184,17, and the unit is watts. Okay, so that is 5.2. Now going back to 5.3. Okay, so it says define the term conservative force. All right, so what is a conservative force? We have conservative force and non-conservative forces. Okay, one is independent of the path taken and one is dependent on the path taken. So yeah, can you guess which is which? Okay, so where am I gonna write that? Yeah guys, I'm still learning how to use new technology. We need to advance. Okay, so conservative force. Okay, so what is it? It is the force. Oof. I don't know what happens. It's like the ink just comes out by force, or maybe it's my force at which I apply the pen. Okay, so conservative force, also known as an internal force. My goodness. Okay, so it's also known as an internal force. Okay, it's actually force for which work is done. So it's the force for which work is done. Okay, force for which work is done. Okay, so this work done involved in moving an object, between 2 points force for which work done in moving force for which work done in moving an object between 2 points is independent of the path taken. So the conservative force is independent of the path taken. Independent of the path taken. Okay. And examples of that would be gravitational force, mechanical energy. It could be a spring force. Yes, spring force, electrostatic force, magnetic forces, things that you can't really see with the naked eye, but you can. It's more internal, hence it's an internal force. Your non-conservative forces, however, they are dependent on the path taken, and that would be like friction. Okay, so friction is the one that comes to mind. Okay, now let us go back to question 5.4. So, is the force which the wall exerts on the ball a conservative or a non-conservative force? So we know that this ball here, the only force acting on it is gravity, right? So the force from the ball to the wall is a conservative force. But once the wall now exerts a force on the ball, what is that going to be? Is it still conservative or is it non-conservative? Okay, guys, so the answer for that, it is non-conservative. Okay, why? Here, the ball, the only force acting on it is gravity. Okay, so gravitational force. Okay, and the energy that it has there, it's actually potential energy. But once it gets into motion, that potential energy starts converting to kinetic energy. So by the time it reaches the wall there, it's pretty much full of kinetic energy. So Newton's is the third law. I'm exposing myself. I forgot. But I think Newton's third law says that if body A acts on body B will exert an equal but opposite force on body A. So this one is coming with an kinetic energy here. Okay. There on the wall. So the wall will exert back with the force that it comes with. Okay, the wall will exert it back. So because we've established that at that point you have a non-conservative force, the wall will also exert a non-conservative force on the ball. Okay, is it a ball? On this wrecking ball? Yes, so hence it is a non-conservative force. If they said the ball, when it is released, is it non-conservative or conservative? We would have said conservative because the only thing acting on it, or the only force acting on it, is gravity. And that is a conservative force. Cool. 5.5. State the energy conversion that takes place during a downward swing. Oh yeah, I've just spoken about it. the energy conversion that takes place during the downward swing of the demolition ball. So basically here, it goes from gravitational, or rather potential energy. We're talking about energy here, not forces, né? So it would be potential energy. Okay, so I'm just gonna say EP, which just says potential energy. So potential energy then converts to kinetic energy, so it converts to EK. Okay, obviously you're gonna write that down in words properly. Okay, and then the last question: using energy principles, calculate the magnitude of the average force exerted on the ball. Okay, exerted on the ball while it moves into the wall. Okay, so we already discovered here from the previous question we have a non-conservative force, right? And do you remember the equation for non-conservative forces? So this is 5.6. So for work done by a non-conservative force is equal to the change in kinetic energy plus the change in potential energy. Okay, and we know that this non-conservative force is 0. Okay, so the change in kinetic energy here, guys, we can, I will say half m, and then the v, you have v final. Okay, what happened there? Final velocity squared minus initial velocity squared. Okay, and then we have mg h. Okay, so we have h final minus h initial. Okay, so let's just go back again. Calculate the magnitude on the average force exerted on the ball. So it's the force exerted on the ball by the wall, right? So we have the mass already. Okay, the mass is 1250. Now the final velocity, guys, obviously the ball will come to a standstill, right? So then we can say the final velocity would be 0. Oh yeah, okay. Sorry about that. Okay, so we have the initial velocity actually. Sorry, let me just go back to this and see the magnitude of the average force exerted on the ball when it moves into the wall. Okay, so actually its initial velocity there, the ball, is actually 0, and by the time it gets to the wall, the final velocity is at its maximum. Okay, sorry about that. So yes, initial velocity is 0, and then we have 1250, that's the mass, multiplied by 9.8. Okay, and the final height, just move up so that we can see. We see that the initial height is actually 5.8, but the final height is 0 because it's back to its initial point. Okay, so the final 5.8. Okay, and that one is 0. Okay, so now we can calculate what the final velocity is. Okay, so I'm just gonna calculate what that whole value is, take it to the other side, and then we'll see from then what we do. Oh guys, sorry, here I was saying, so initially it was at 5.8, but finally it gets to its original position, so I just confused the two. All right, and then let's just calculate. Okay, so we have 1250 times 9.8 times negative 5.8 5,8, and that is negative 71,050. Okay, and I said I'm going to take this value to the other side of the equal sign, so it'll be positive 7150. So yeah, 7150. Okay, and we can see here we can divide it by a half. 1250, and we have our final velocity squared. If we want the velocity, final velocity, then we can root all of this. So we can put all of this in the calculator and then determine what the final velocity is. Okay. So we have 71,050 okay, divided by half times 1250, and that would be 10,66 meters per second. Okay, so we just got the final velocity, guys. The question was for us to calculate the average force, right? Let's just make sure. Yes, calculate the magnitude of the average force exerted on the ball while it moves into the wall. Okay, so now again we're getting back to our work equation. So the work done will be your average force times distance and cos theta. That is your normal equation. And here I think I didn't read this out, but they gave us more information. So they said the demolition ball is released from point R and strikes the wall at the lowest point of its swing. So demolition, yeah, this is what I should have read actually, released from point R. So that's where we know that the initial velocity is 0, and strikes the wall. Okay, we just calculated it, strikes it at a velocity of 10,66 meters per second at the lowest point of its swing. Okay, so finally the height was 0 and initially it was 5,8. Now the ball then moves 0,2 meters horizontally into the wall before coming to rest. Okay, so if we're looking at, yeah, it then moves. Okay, so they gave us 0,25. Okay, it's quite small, but we could say at that point that is 0,25. Okay, so we then have the distance that is required. Okay, looking at our D, that's going to be 0,25. Our average force is what we're looking for. The work done, well, the work done there, it would equate to kinetic energy. Okay, remember you can say that the work done would equal to the change in kinetic energy. Okay, and we're looking for the average force. The distance there is 0,25, and now theta. What would theta be? Okay, so you have this force that the wall exerts on the ball, right? So it says calculate the magnitude of the average force exerted on the ball. This ball is moving to the east. Okay, so it's moving to the east. Okay, and for us to use cos 0, then the force applied would have to be in the same direction, but that's not the case. The force applied is actually moving in the opposite direction, and then the angle in between where the ball is going and where the force is applied, it's actually 180 degrees. So we can then say multiplied by cos 180. Okay, and our kinetic energy there, it's actually half m v squared. Okay, so we already know our final velocity is 10,66 squared, and our initial velocity is 0. Okay, so all of that kinetic energy is divided by 0,25 cos 180. Okay. Yeah. Actually, the final velocity is 0 because it's going to come to a standstill. All right. So the initial then would have to be 10,66 squared. It's not fitting. Yeah. So 10,66 squared. Alrighty. Yeah. I hope you get it. Okay. They did tell us that the ball eventually comes to a standstill. So it's released from point R, which was 0, strikes the wall at 10.66 meters per second to its swing. The ball then moves 0.25 meters horizontally into the wall before coming to rest. So there's the final velocity being equal to 0. Hence we substitute 0 there. And now we can then put this in the calculator and call it a day. Okay, so we have 10,66. All right. So I have a half times 1250 multiplied by 0 minus the answer squared. Okay, and that is all over 0.25 multiplied by cos 180. Okay, and our answer is 284,200 newtons. Okay, 284,200. Alrighty, so we have average force, $284,200 newtons, or you could have said 284,2 kilo newtons. Anyone would work. Okay, so yeah, that is it, guys. We've completed question 5. Ooh. And yeah, I hope you understood. If there were some things that were not clear, please do comment in the comment section. Otherwise, you can book a session. You can go to our website www.mptutors.co.za, and then you can also set up an appointment on WhatsApp as well on 076-312-1107. And we look forward to hearing from you. We look forward to your engagement. Please do tell us which papers you want to do, what questions you want us to help you with here on YouTube. But otherwise, yeah, it's goodbye from me. Thank you. Hello everyone, and welcome to MV Tutors. I'm Tsolo, and I'll be looking at the Physics Paper 1 exam that was written in June. So yeah, let's get right to it. Guys, don't forget that if you would like a private lesson, please do visit our website on www.mvtutors.co.za, or else you can set up an appointment through WhatsApp on 076-312-1107. Okay, all right, let's read what question 6 is saying. Okay, so a learner in a car moving at a constant speed of 10 meters per second along a straight horizontal road records the frequency of sound emitted by a distant stationary source. Okay, so we don't know where the source is. Is it in front of this moving vehicle? Is it behind? But we'll see as we read further. The learner then repeats the recording of the frequency of the sound when the car travels at a new constant speed of 20 meters per second. The graph below, not drawn to scale, is obtained from the results. Okay, so let us see what this graph is showing us. All right, so we can see here at 0, well, when the learner is stationary, there's a frequency of 700 hertz. And then at that constant speed of 10 meters per second, there's a frequency of 679.1 hertz. And then at 20 meters per second, it is 658.2 hertz. All right, guys, so the frequency is decreasing. What does that tell you? It tells you that this person or the student is moving away from the source of sound. Okay, remember, if you have like a source, okay, so you have a source of sound, right? And if the waves keep getting bigger. Okay, yeah. Actually, let me just remind you of this equation. Speed is equal to frequency times wavelength. Okay, so then if you would want to know the frequency would be the speed over the wavelength. Now, when you increase the wavelength, I'm looking at what I'm writing. Yeah, so when you increase the wavelength, definitely your frequency will decrease. And the increase in wavelengths, okay, that just tells you that you are far away from the source. If on the other hand you were near the source, the wavelengths would really be very small, and then you would hear a higher pitch or a higher frequency. Okay, so the smaller the wavelengths, let me just use a different color. Yeah, so the smaller the wavelengths are, or the distance between the wavelengths, then the higher the frequency will eventually be, or the higher the pitch. So that's something that you just need to understand. So by looking at this graph, I can tell that this person or this student is moving away from the source of sound. Okay, let me just remove that and let us read the questions. Okay, and just move this a bit up. All right, so the first question says, state the Doppler effect. Okay, guys, those of you who watch our videos, we've been doing Doppler effect. So you should know by now, but let me attempt to write it here on the screen. So the Doppler effect is really the change in frequency or pitch of sound detected when a wave source and the observer or listener are moving relative to one another. So if one is stationary, one is moving, what frequency can you detect? Basically, that's that. If both of you are moving, again, what frequency can you detect? So let's just write it down for 2 marks. Okay. I'm using red. No, I don't want red. I like using the blue ink. Okay. Okay, so what is the Doppler effect? It is the change in frequency I'm getting used to write on this thing. We got this new thing called Wacom where you write there, so sorry for my horrendous handwriting. So it's a change in frequency or pitch. Okay. Yeah, change in frequency of sound. I'm just gonna write on the side. Of sound detected when a wave source and the observer, okay, and just right here, when the wave source and observer or listener, what happened there? Yeah, observer or listener are moving relative to one another. Okay, moving relative to one another. Oh gosh. But yeah, so that is that. Okay, so 6.2.1, it says write down the frequency of the sound emitted by the stationary source. So we already know the frequency that the learner detected when he recorded, right? We know at 10 meters per second it was 679.1, and at 20 meters per second it was 658.2. But what is the actual frequency emitted by the stationary source? Okay, so the key thing here to look for is for you to get the true frequency emitted, or the sound emitted, is for both thus the learner and the source to be stationary. So when the learner is stationary, the recording, it recorded 700. So basically the information that we have is from 10 to 20, but through extrapolation of this data, so this data was extrapolated to then get what the actual frequency is of the source. So it is 700 hertz. Okay, and then they want to know, why do we say that? It is because both the listener and the source both the listener and the source are stationary. Okay, stationary. Okay, now let us move up. Okay, in which direction is the car moving relative to the source? Okay, definitely moving away. All right, and give a reason for your answer. Well, like I have stated, the frequency decreases, okay, from 10 meters per second. So as this person continues moving, the frequency was decreasing. Okay, I hope you understand that. And we saw that on the graph, it was illustrated there. So as he went from 10 to 20, the frequency did decrease. And I did say that when a source is actually far away from the listener, the wavelengths, the distance between the wavelengths are actually, distance between the waves are actually quite spread out. And if they are big, then you have a small frequency. So and then finally, calculate the speed of sound in air. So they normally give us this number. It is around 340 meters per second, but now they want us to calculate it. Okay, so we're going to use the equation. All right, and the equation says the frequency of the listener is equal to the frequency of the source multiplied by the speed, that's the speed of air, and then we have plus minus the speed of the listener all over speed air plus minus the speed of the source. Okay, so now which is which? Do you choose a positive or a negative here? And also at the bottom. Okay, so let's just put in what we know. You can choose, looking at the graph, which one you would like to go with. Do you want to go with the speed of 10 and a frequency of 679, or do you want to go with the speed of 20 and a frequency of 658.2? Both will yield the same answer. I'm going to go with the speed of 10, right? And a frequency of 679.1. So 679.1, that is what the learner heard. Okay, so 679.1, and the frequency of the source, well, we did establish that it is 700, right? And then I'm just gonna put brackets here. This is what we are looking for. Okay, and the speed of the listener, I chose 10. Okay, you could have gone with 20, but if you go with 20, then you need to put the associated frequency. Okay, again, this is what we're looking for, and we know that the speed of the source is actually 0 because it's stationary. Okay, now again, what do we put? Plus, minus. So if the listener is moving away from the source, then you're going to put a negative. Okay, if the listener was moving towards the source, then it would be positive. And here it doesn't really matter whether you put a positive or not because it's 0. Okay, I'm just going to put a positive just for the sake of calculating. Okay, even if it's a minus, it doesn't matter. All right, and then let's simplify this. All right, so we have 679.1, and that will be divided by 700 if I take it to the other side. And then we have v minus 10, and that's all over v. So now I'm going to take v to the other side. So I still have 679.1 over 700, and that would be multiplied by v. And this side I have v minus 10. Okay. Let us see now. What am I going to do? I will then take v to the other side. Yes, because I want the v's together. Okay, so I have again 679.1 over 700 v minus v is equal to 10. All right, and then I'm just gonna put it in the calculator, and then we're gonna see what we work it out to be. Okay, let me just get the calculator. Okay, so we have just clear that. We have 679.1 all over 700. Okay, this thing doesn't want to go down. Oh, there we go. Okay, over 700, and I am subtracting 1. Okay, so I get, oh gosh, such a big number. Okay, so I get negative 0,0298. I hope I forget it. I remember it. So negative 0,0298. Okay, negative 0,0298. Okay, so there are many values here, and that is equal to 10. Now if I want v alone, sorry, I've been forgetting this negative here. So if I want v alone, it'll be negative 10 all over negative 0,0298 and all those other values. And then ultimately, ladies and gentlemen, what will be our answer? Oh no, it didn't take it, didn't save it. Okay, let me start again. Oh, okay. It's actually here. Yes, there's my answer. So I can then say negative 10 divided by the answer, and we get the speed. So it's not exactly 340, but we can see it's quite close. So 334,93. Okay, 334,93. So there it is. Oh, okay, something happened. Yeah, 334,93, and that is meters per second. And that is our final answer. So yeah, that is it with question 6. Alrighty, so let us get started with question 7. Alright, it says two charged spheres R and S are both stationary. Okay, stationary, they're not moving, they're not accelerating. On a smooth, okay, another thing, there's no friction. On a smooth insulated surface inclined at an angle of 25 degrees to the horizontal. So here's the image below. You have the two spheres R and S, and here's the 25 degrees inclination. Okay, sphere S of mass 0,01 kilogram and carrying a charge of negative 6 times 10 to the power minus 9 coulomb is connected to a 0,03 meter long light inextensible string. Wow, what a description. Attached to point P at the top of the incline. So here, there we have point P there, and there's the string. Okay, probably the mass of the string is negligible. All right, and then sphere R carrying a charge of 5 times 10 to the power minus 9 is held such that the distance between the centers of the spheres is R, as shown in the diagram below. And again, they say ignore the effects of friction. That we already knew. All right, and then sphere R exerts an electrostatic force of magnitude 1, 2 times 10 to the power minus 3 Newton on sphere S. Okay, as you can see, there's like a positive charge, that's a negative charge, so there is a force of attraction there, and that is the magnitude of that force. Now, 7.1, state Coulomb's law in words. Okay, guys, and that is 2 marks. So, let's see. A nice way of actually remembering how to write out Coulomb's law is to put the formula there, okay? And that is the formula. So the force that one charge actually exerts on another, okay, you have your constant K, which is 9 times 10 to the power 9. Then you have Q1, in this case it's R and S, so I would say QR, and then QS, and R squared. So just by knowing this formula, which is given in the formula sheet, it is easier then to write out Coulomb's law. Okay, so what is Coulomb's law? Coulomb's law is the magnitude, né? The magnitude of the electrostatic force, first of all. So you're going to say the magnitude. So magnitude, okay, of so the magnitude of the electrostatic force the magnitude of the electrostatic force that one charge okay that one charge has on another charge. So yes, the force, or rather the magnitude of the electrostatic force that R has on S, okay, that magnitude is equal to, so now we're here, is equal to the product it's equal to the product of the two charges, or rather the product of the magnitude of the two charges. Okay, now this is becoming an essay. Product of the magnitude of the two charges, and you can see on the equation we're going to multiply the charge of R and the charge of S. So the product of the magnitude, and by magnitude we're not taking sign into consideration when you're calculating force. Okay, so it's equal to the product of the magnitude of the two charges okay. So yes, the magnitude of the electrostatic force that one charge has on another is, it's actually directly proportional. Sorry about that. It's actually directly proportional. Is directly proportional to, so that sign there, that's what we use to say directly proportional. So the magnitude of this electrostatic force is actually directly proportional to the product of the magnitude of those two charges, and indirectly proportional to the square of the distance between them. Okay, so that was a mouthful, but just to rephrase, the electrostatic force, okay, the magnitude of the electrostatic force that one charge has over another is directly proportional to the product of the charges, and inversely proportional to the square of the distance between them. Okay, so that is 2 marks. Now let us go back to 7.2. Calculate the distance r between the spheres. Okay, we already have the formula. They gave us the force, which is 1, 2 times 10 to the power minus 3 Newton. We have the constant, it's 9 times 10 to the power 9. We have the charges, okay, of both spheres, okay? They gave it to us. There, 5 times 10 to the power minus 9. Negative 6, you can say nanocoulomb because it's times 10 to the power minus 9. And then our only unknown there would be R, which is what we need to get. So let us do it. So 7.2. Again, the formula F is equal to K QR QS all over R squared. And R squared is what we're looking for, so I'm going to make it the subject of the formula. So R squared is equal to K QR QS all over F. And finally R, when we get it, it'll be the root of K Q R Q S K all over F. And now we can substitute what we know. Alright, so K is 9 times 10 to the power 9. And then you have QR. I forgot the values. Okay, so R is 5, and then S is negative 6. Okay, so 5 times 10 to the power minus 9. And remember we said we're only using the magnitudes. Okay, so you don't put in the negative sign. So it's just going to be 6 times 10 to the power minus 9. And that is all over the force, which was 1,2 times 10 to the power minus 3 Newton. Okay, and all of that is under the square root. And then we're just going to use our calculator to calculate that. Okay, actually, this is taking up a lot of my screen space. So I'm just going to put it on the side. Okay, cool. Now we have space. Okay, square root fraction 9 times 10 to the power 9 times 5 times 10 to the power minus 6, and then times 6 times 10 to the power minus 9, and then that is all over 1,2 times 10 to the power minus 3. Okay, did I write this correctly? Oh, sorry, here I wrote times 10 to the power minus 6. Okay, and there we go, our answer 0,015 meters. Okay, 0,015 meters. If they do say round off to 2 decimal places, then it will be 0,02 meters. But going forward, if you're going to use this value, please use 0,015 and not the rounded off one, or else your answer will be off. Alright, and then 7.3, draw a labeled free body diagram of sphere S. Okay, I'm just going to copy this below so that we do not have to continue going up. Okay, so now we need to draw a free body diagram of sphere S. Okay, I'm going to attempt to do it on the sketch itself and then make it a bit clearer below. Okay, so here's S. We're going to indicate that with a dot. First of all, we have the force of gravity acting on it. Okay, others would put W. Then normal to the surface or perpendicular to the surface, we have the normal force. Okay, and then remember we had that force due to R. Okay, this one, so the electrostatic force, I'm just going to say Fe. Then we have the tension force going up there. Okay, so yeah, force of tension. And then I'm going to resolve the gravitational force, okay, because it is not in line with this new y-x axis. Okay, we need it to be that way, so we need to resolve the force of gravity. So we're gonna have that component there. Remember, that's our angle, I'm just going to say theta, but we know it's actually 25. So here, because our force now, okay, it's adjacent to the angle, that will be cos. So we have FG cos 25. And then we resolve it again here. So we have two forces this side, and that will be FG sine theta. And theta is actually 25. Okay, so that is our free body diagram, a labeled one at that. Okay, now they want us to calculate the tension in the string. So let us do it. Okay, so I'm going to calculate the tension in the string. Remember, we had tension there. We had the electrostatic force. We also have another force there, which was Fg sine 25. Okay, I'm not going to look at the vertical forces. We don't really need that. Okay, so if I sum up, this is 7.4.1. If I sum up all the forces in the x direction, that should give me 0. Remember, there's no acceleration. Remember, your formula there is F is equal to ma, and since acceleration is 0, F is equal to 0. So all the forces in the x, the net force actually, they are equal to 0 when you sum them all up. Okay, so since that's the case, we have the force due to the tension. Okay, I'm assuming that going right is positive and going left is negative. So we have positive tension force there minus the electrostatic force minus the gravitational force. Okay, and that is equal to 0. Okay, now we need to know what the force of, or the tension force is. So I'm going to just take the other forces to the other side. So here's the electrostatic force, and here is the gravitational force. Okay, now we can write down values. Okay, so the force of tension, the electrostatic force, it was 1,2 times 10 to the power minus 3. And then the gravitational force, that is m times g. So m, they told us it's 0,01 kg, and g is just 9,8. Okay, and then we have sine 25. So then we can calculate what our tension force is. Okay, so we have 1,2 times 10 to the power minus 3 plus 0,01 times 9,8 times sine 25 degrees. And our answer there is 0,0387. Okay, so yeah, that is Newton. And if we were to round up to 2 decimal places, 0,04 Newton. Okay, now let us answer the last question. So calculate the net electric field at point P. So there is our point P. We need to know what the net electric field is at that point. Okay, so remember the equation for the electric field. E is actually equal to F over Q. Hence, your unit would be Newton per Coulomb. Okay, and we know that our force is actually the constant K. Then you have Q1, and you have Q2, and over R squared. Okay, that's the F part of it. But you still have this Q, so we need to put it down. Okay, and if we simplify it, one of the Q's are going to cancel out, so you're only left with one Q, R squared. So that is actually your formula. Okay, and if you are looking for the net, E net, you're going to have to add them all up. So E1, E2, until. Okay, so now they're asking for the net electric field at point P. So what is actually affecting P? It's actually both R and S. Okay, so yeah, so E net, or net electric field, it's actually going to be that when P is affected by R, and also when P is affected by S. Okay, and then putting our equation there, we're going to have K, Q due to R, and R squared. And then we're going to have again K, Q due to S over R squared. So you can see that K is actually a common factor, so I'm just going to take it out. Then I'm left with the charge due to R, and that distance between R and P, the charge due to S, and that distance between S and P. Okay, so K, as we've said, it's actually 9 times 10 to the power 9. Okay, now what is the charge due to R? So okay, on this question, guys, you will have to, if you have a negative charge, you need to put there that it's negative. Okay, so this is where you need to consider the sign. Okay, so R, it is positive 5, and S, it's negative 6. Then the distance between R and P, remember we calculated that small r, which was 0,015. So the distance between R and P will be 0,015 plus 0,03. But the distance between S and P, it's just going to be 0,03. So yeah, let's go ahead and write it down. So R, it's positive 5, okay, times 10 to the power minus 9. And we said the distance will be 0,015 plus 0,03. That is squared. Okay. Then you have S, which was negative 6 times 10 to the power minus 9. And that is just going to be 0,03 squared. Okay, so I'm just going to plug all of that in the calculator. Okay, so we have 9 times 10 to the 9, and then we have our brackets, and we have that plus that. Okay, so for the first one, we had 5 times 10 to the power minus 9, and the distance was 0,015 plus 0,03, and all of that is squared. Okay, second one, we had negative, okay, here we had negative 6 times 10 to the power negative 9, and that is all over 0,03 squared. Okay, and the answer is negative. Okay, so the answer is negative 37,777,78 Newton per Coulomb. Okay, now we need to say what the negative sign actually means. Remember, in the sketch here that I drew, we indicated positive as moving up, or rather positive moving towards P, and negative as going down. Okay, so if we have negative here, it means the electric field is actually towards the charged spheres. Okay, or we could say it is away from point P. Okay, so it's really up to you how you're going to interpret that. And I want to write this number out using scientific notation. So I'm just going to take the comma this side. So 1, 2, 3, 4. So my final answer is going to be 3, Okay, let me just say 3,78 times 10 to the 4 Newton per Coulomb. I'm going to choose away from point P. Okay, so yeah, away from P. And that is it. We are done with our lesson. That was the final question. So I'm just gonna call my husband to come and do his section. Thank you. Enjoy the rest of your Saturday. You ready?
Yeah. You playing the advert?
Oh yeah, let's play an advert.
Yeah.
See you guys later. He needs to go take off his gown.
Well, good morning, ladies and gentlemen. As you can see, I've changed a few things with my what do you call this, view. Okay, my wife is left-handed, so she was writing from the left, and I'm right-handed, so I had to change it all around. Okay, but it's of little consequence to you, I'm sure. Right, so here we go. I'm going to be doing this question. This is question 8. As you can see, I've also just quickly added my question right after where she finished. Okay, so this is question 8 of the 2021 June exam. You wrote this just a few weeks ago, and I'll be doing the memo for this question. Well, I'm assuming by now you already know the theory and the principles required to answer such questions, but in the event that you don't you worry, I got you. Okay, we're gonna recap as we go. All right, so without any further ado, let's read the question. Question says, three resistors are connected to a battery with an unknown EMF and unknown internal resistance as shown below. Well, as you know, an EMF, let's just assume, is a battery. It can be a battery, okay? So it has its own internal resistance, okay? So in this case, they're not giving us what that internal resistance is. They're not also not giving us what the EMF is. So let's see what kind of questions they want. Ignore the resistance of the connecting wires. All right. Question 8.1. In the definition of EMF of a battery given below, okay, so it's a battery. It is a battery. It's not like a battery. Given below, A and B represent missing words or phrases. Okay, so it says the EMF of the battery is the maximum maximum energy. Okay, well, I like a red pen. My wife likes blue for some reason. I prefer red. So this is gonna be 8.1, and it says the EMF of a battery is the maximum A. We're talking about energy here, so it's gonna be energy. Okay, supplied by a battery per unit charge. Okay, so this is just definition stuff. Unit charge. Okay, so that's it. That's just a straight definition of EMF. Now let's continue with this. With switch S closed, let's go ahead and find S. Aha, there is S over there. So what's happening there? Okay, so what's happening there is that the switch is closed. Now, what happens when switch is closed? Okay, I want you to go with me here. Always pretend that electrons are actually flowing like water. Imagine it's a stream. Imagine it's a stream of water. Sorry, it's cool. It's my light. It's a bit dark in the morning, so we needed extra light to just make this video richer and you can see us clearly. Okay, so what's happening here? I was saying that imagine that the electrons are like water, they flow. Okay, current is flowing like water. Well, if you think of it, if you think of the sea, those are currents that are coming in at the beaches. The beaches. The beaches. Yeah, pronunciation. Anyway, imagine current, water is flowing. So when the battery is going, there is water current going here, here, and then it branches off here, and then some of it branches off here, and then when it's closed, branches off there. So it is like it's flowing like that. Okay, now the reason I made it flow this side is because this is the positive side of the battery. How do I know? Because this long stick here, that long stick represents positive, and a shorter one there, it represents negative. Okay, and then current will flow from positive and then like that. So if it's closed like that, it means we must consider both of these resistors. Now, how do you think of resistors? Think of a resistor as a light bulb. Okay, so when you switch the light on, current is flowing there. We've got total current there coming from the battery, but now as soon as it branches off here, we've got current 1. Okay, some of the water goes there, or some of the energy goes there, and current 2. Okay, so the total is current 1 plus current 2. And then so both, if it was closed, then the total current would be equals to current 1 only. But if it was open, the switch was open, but it's closed, meaning that current is flowing through to. Now that means that if we are to calculate the external resistance, external means the total resistance, we need to consider both of these these resistors. So let's just go ahead real quick. 8.2. Okay, external. So we've got first of all, these are in series. Okay, 4 and 3 are in series, so the resistance in series is equals to the first one was 4 plus 3, which is equals to 7. Okay, we're not done. That's not the total resistance or external resistance. We've got another 7 here, which is in parallel with this 7 that we got here. Okay, now if you remember parallel, how to calculate parallel resistors, it's 1 over Rp, and it's equals to 1 over E7. Okay, so that's it. 1 over 7, which is the first one, and then we have a second one, so we're gonna add that right here. 1 over 7. Wow, now we need a calculator. So I'm just gonna move my camera this side so that I can access my camera. Oh, my wife left this, didn't clear it. I'll just clear it, put it this side. So we've got 1 over 7. Let's put fraction 1 over 7. We've put 7 down there. We'll go to the side, plus put the fraction again, 1 over 7. Okay, so check this out. We get that 1 over RP is equals to, I wonder if I can put it in fraction form. That's 2 over what? 2 over 7. Nice. So it's 2 over 7. Okay, now I need to solve for my RP. So what I'm going to do is, everything's on the way now. Let's put the camera right there. Okay, so we'll do some mathematical gymnastics. I heard that from someone else who teaches science. Okay, so RP then is going to be equals to the reciprocal of this, which is 7 over 2. And 7 over 2, let's just calculate that. 7 divided by 2, that's gonna be 3.5. Okay, so that's 3.5. Okay, now this is our final answer. Now I want to ask you something. What are the units of resistance? Okay, I'm going to leave that there, assuming that you are in metric and you already know what they are. I'll come back to them later, but comment on the comment section and tell me what the unit I'm supposed to put over here. What's the unit for resistance? Okay, let's move on. Now let's go to 8.3. 8.3.1 says calculate the internal resistance of the battery. That's going to be 8 marks. Wow, that means we've got a whole lot of work to do there. 8 marks, that's a lot. But let's just check it out. What do we need? What do we have? Okay, first of all, they said, okay, switch S is opened and the voltmeter is 2.8. Here, switch S was closed and the voltmeter was 2.63. Now, that's a clue right there, ladies and gentlemen, that we can actually have two equations and then solve it simultaneously for the internal resistance. Now, if you actually check your formula sheet, and then you check the EMF formula, you're going to get something like this, that the EMF is equals to the current, open brackets, external resistance plus the internal resistance. Okay, so now the EMF is going to be the same. It's always going to be the same because the battery doesn't change like that. It's always going to be the same whether the circuit is closed or open. However, the current might not be the same. It's not going to be the same. Also, the external resistance is not going to be the same because that's now affected whether the circuit is open or closed. So the two equations I'm going to have demonstrate, number one, what happens when the circuit is closed. Okay, so when the circuit is closed, that's the original scenario we had here, where the water is flowing on both of the parallel stuff. So there, what we have is that the EMF is going to be equals to a different I current. Okay, now we need to solve what current is going to be there when the system is closed. So what am I gonna do? Let me just solve that current first. Now there is this little triangle. Okay, it has V there, and then it has I and R there. Okay, all it's saying is that if you want to solve for volts are equals to I times R. If you want to solve I, which is current, gonna be equals to v over r. Likewise, if you want to solve for r, it's gonna be v over I. So right now we are interested on the I. Okay, so that's gonna be v over r. Okay, so what's gonna be our v? Our v is the total voltage in the closed system. Okay, and let's check that out. We are given over here. Okay, and it's closed, the voltage is 2.63. So we'll put 2.63 right over here. And now, what is the total resistance? It's the one that we solved above here, which is the 3.5. Okay, so 3.5. All right, so let's quickly put that in the calculator. What do we have? We have 2.63 divided by 3.5. So that's going to be equals to 0.75. Let's just take 2 decimal places. Okay, now that is what's happening when the system is closed. Okay, should I continue or should I do when the system is open? Let me do open right now. Okay, so now this side, let me use a different color. Let's go purple. Now, what happens when the system is open? When the switch is open? Okay, so that means that the switch S is open like that. So no current is flowing to the 7. That means now, if I'm to, just demonstrate this using this highlighter, the water is gonna go like that, and like that. That's it. Well, technically it will go like this too, but it will get blocked there. It's not being used, so it will go back and come here. So the only resistors in play are these ones, 4 plus 3. Okay, that's it. So likewise, same calculation. It's gonna be I. Oh, my bad. I need to go back to the pen. It's gonna be I is equals to V over R. The V in this case we are given as 2.8 for open. So we've got 2.8 divided by the R. As you can see there, the total resistance now is no longer 3.5 because the parallel is not at play, but only these ones. So it's 4 plus 7, only the ones in series. 4 plus 3, which is equals to 7. So that's our total resistance there. Okay, so let's go ahead, put this in a calculator real quick. What do we have? We have 2.8, and that's going to be divided by 7, and we get 0.4. All right, so let us continue. Let's continue this side. So now our EMF equation is such that we have I, let me just rewrite it, I and big R plus small r. Now for our I, we have that it's 0.4. Our big R, it's the same one, it's 7 plus small r. That's it. That's it. Now this side, on the red side, what we have is a situation where our EMF is still the very same equation. It doesn't change, just different variables. Okay, our I this side is 0.75, and then our our external resistance is 3.5, and then the internal resistance is the same, as well as the EMF. It's gonna be the same. There's many ways of calculating it, but it's gonna be the same. So what we're gonna do now, we're gonna equate the EMFs. So let's say this one is called equation number 1, this one is called equation number 2. So what we're gonna do is that we're gonna take equation number 1 and equate it to equation number 2. Right, so what's that gonna look like? It's gonna be equation number 1 is 0.75, and then we got that 3.5 plus R. That's gonna be equals to this other one, which is 0.4. We got 7 plus R. Okay, so now all that's left is just to do some mathematical gymnastics, and then we're gonna get the answer. How we're gonna do that? We're gonna take that, multiply it there and there, take that, multiply it there and there. Okay, so the first one is gonna be 0.7 0.75 times 3.5, and I get 2.625 plus, if I multiply that one, I'll get 0.75 R. That's gonna be equals to, let's do that one now. Yeah, just put it there. It's gonna be 0.4 times 7, and then I get 2.8 plus that times that is 0.4 R. Okay, so what I'm gonna do, put R's on one side, numbers on the other side. So I'm gonna put the R's this side, so it is 0.75 R minus 0.4 R. That's gonna be equals to 2.8 minus 2.625. Okay, need the calculator once again. This screen is just too big. I need space. Okay, so now it's 0.75 minus 0.4. That's gonna be equals to 0.35 R, which is gonna be equals to 2.8 minus 2.625. So that's 0.175, and then my final answer, divide both sides by 0.35. So I'm just gonna divide that answer by 0.35. So my final answer is 0.5. Okay, so that is my final answer. Now, once again, what are the units for this? Let me know in the comments section. Okay, but I'm just gonna go back here. When I asked you to let me know for that, what did you say? Did you say ohms like that? Yeah, it must be ohms, because I mean it's still resistance. Oh, they are given in ohms. Look at that. They are given in ohms. So be consistent. Right. So tell me what answer is that. Put the units in the comment section. All right. What's the next question? Let's go check that out. So we've solved the internal resistance. Now we need to solve the EMF of the battery. Oh, well, we can take any of these equations. We'll take both of them just to demonstrate to you that both of them will work. So let's use equation number 1. Equation number 1 is 0.75 EMF is equals to 0.75, 3.5 plus, now R, we've solved the R, 0.5. Okay, let's see what answer we get there. We'll put that in a calculator. So we got 0.75, open brackets, 3.5 plus 0.5, close brackets. I get 3. What are the units there of EMF? Let me know in the comment section once again. Now let's take equation number 2. Let's see, number 2. It was in purple, so I'm gonna stick to purple, and it's this one. So it's 0.4, open brackets, 7 plus R. We've solved the R, it's 0.5, so I'm going to put that there. Now all that's left is to put this in a calculator and see what answer we get. 0.4, open bracket, 7 plus 0.5. Close that. Well, look at that. The EMF is 3. It's the same answer, guys. Remember, a battery, it comes standard. Okay, it has one EMF and it has one internal resistance. Both of them pretty much don't change. Now, what are the units of EMF? Okay, now let's come back here. Internal resistance. Okay, internal resistance, if you said, let's put that in red, if you said it's still resistance, so it's ohms, then you are absolutely right. Now EMF, if you understand what EMF is, you will know that the units for EMF is just, what is that? Volts. That's it. Well, ladies and gentlemen, we are pretty much done. That's it for today. Catch us next week again for this session. We will continue on this exam paper. We'll pick another question. Okay, but just in case you are interested in a session with us, a private session, one-on-one, we are available. You can just comment under this video. Visit our website www.mvtutors.co.za. book yourself a session in there. Book a free consultation. We give you free consultations so that we can assess you, assess whoever needs the session. Okay.
Bye, everyone. Listen, oh, there it is. Okay, enjoy the rest of your weekend. Yeah, it's a wrap from us.
That's it.
Got
Okay.
to take off my things.
Yeah. Oh, also we'll be interviewing someone a little bit later on. So wait up for that. It's gonna be interesting. You're gonna enjoy it. We're gonna be interviewing another student, so stick around for that. We'll keep you posted. Bye for now. Well, welcome to MV Tutors. It's a cold day here in Pretoria today, but we're gonna do this recording for you because we like to help. Well, my name is Figa, and if you'd like a tutorial session after this, then feel free to visit our website on www.mvtutors.co.za. Alternatively, you can just comment under this video asking for one, and we'll be glad to assist you. Well, without any further ado, let me just move my camera to the side right there. Okay, now what are we doing today? Today we are doing the paper 1, physical science, and this actually is if you look here, check this out. I just increased my screen. That is not what I wanted to do. Well, let's try decrease it. There we go. Now what I want to do is just show you that this is the 2021 June paper. So you just wrote this, okay? This is what you just wrote like a month ago, a few weeks ago, since this is July at the time of this recording, and this exam was written just a few weeks ago. So we are doing the memo. Okay, now I believe we'll be the first ones on the internet to take this out, so looking forward to that. Okay, anyway, let's get right into it. Okay, well, I prefer my camera on the left. Is this left or right? I don't know, but I'll just leave it there. And then what I'll do is that I'll take this a bit down, or I'll take it this side just to create more space. All right, now question 9. This is question 9. So we're doing the entire paper 1 and paper 2. This is just question 9 of it. It says the diagram below is a simplified representation of an AC generator. Very important. The coil is rotated in a clockwise direction in the magnetic field. Okay, as you can see. Now, write down the name of component X. Where's component X? There. What do you guys think this is? I hope you did this in class. But in the event that you didn't, I'm just gonna write it here. Let me use a red pen. I prefer a red pen. So let's go ahead. We call this a slip ring. Okay, just like that. Slip ring. Okay, it's a slip ring. Good. Now it says write down the function of component Y. Where's component Y? There it is. These ones, as you can see, is on the outer side of the slip ring. So its job really is just to transfer, okay, just to transfer the current to the outer part of this apparatus. So let me just write that nicely for you, and in a way that will actually make sense. So I'm going to say that it transfers current. Let me create more space for myself so that I have enough space to write. But it transfers current to the outer circuit. Very simply to the outer circuit. Okay, just like that. That's all it does. That's its job. And then use the relevant principles to explain why an EMF is induced in the coil when the coil is rotated in the magnetic field. So I want you to think of this. Okay, when you rotate the coil, okay, why is an EMF induced? Now it's induced because, let me just write it down. Then I'll explain it once I've written it down, because it will make much more sense to you once it's actually written down. So I'm going to say well, according has two C's, right? According to the principles the principle of electromagnetic induction. According to the principles of electromagnetic induction, what does this principle say? It says an EMF, okay, an EMF is induced, okay, as a result of the change in the magnetic flux, linkage. This is not leak age, it's link age. So how can I explain this? If you can imagine a box, and then your matches, you take a matchy and you take it, you whoosh like that on the box, and then fire is created. So it's the same principle here, in that as the linkage between the magnetic flux, the linkage between the two elements of the magnet, rather, or the coil, or whatever is going on there, as they link each other and touch each other, current is created as they change, okay, as there's a change in that magnetic flux. Just like there's a change in the linkage of the matches and the box. As long as there's a change, there's a fire being created. When there's a change, there's a fire being created. Likewise here, when there's a change in the magnetic flux linkage, the link between the matches and the box, then an EMF is created. Well, you can say EMF, or you can say current. Okay, so a current is created when there's a change in the magnetic flux. Okay, well, I hope I try my best to answer that. Now, this one says 9.4, the coil rotates clockwise from the position shown in the diagram. In which direction will current be induced in segment PQ of the coil? So where's that segment? There's P, there's Q. Okay, choose P to Q or Q to P. Okay, so I don't know whether your teacher taught you the left hand rule or the right hand rule, but either one of them can work. You just have to stick to what your teacher taught you. But I'm just going to use my left hand. So it's going clockwise, so then I do it like this, okay? And then I know that if it's like this, then my what's it asking for? Which direction will current be induced? Okay, it's going towards from P to Q. So that's my answer. My answer is P to Q. Okay, P to Q. Alright, that's my answer. Simple as that. Okay, let's go to the next question then. It says the output voltage versus time graph below was obtained for the above generator. Okay, output voltage here, it's on the y-axis. Its maximum is 311, minimum minus 311. It actually looks like a sine graph. Sine graph, if you remember trigonometry. But anyway, all right. And then it says the output voltage is generated at frequency 50 Hertz. Okay, calculates the time t indicated in the above graph. Okay, so I want to highlight something here. I want to highlight the entire the graph, its entire revolution. Okay, so it revolves. This is an entire, it finishes there before it starts repeating itself. Okay, so that is a full graph, and then let's do the next one, and then it starts again. Time t is there. And you see that this green one is actually half of the blue one. That means then that our time t from here to t is actually 1x plus a half x. Okay, now what is x? We need to solve x. X will be the time. Now, solving time, the only way we can solve time given the information we have is using the frequency. Remember, time is actually 1 over frequency. Okay, so here we'll have 1 over 50. All right, now I need to bring in a calculator to calculate this. So what I'm gonna do, I just need to come out of here and fetch my calculator right here. Where's my calculator? Calculator, where are you? There you are, right there. Okay, so there's our calculator. It looks exactly like the one you are using. You should be using this calculator in high school, in metric. So we have 1 divided by 50. And then I don't want it in this form, I want it in that form. 0.02. Thank you very much. So our t is equals to 0.02. Okay, let's put it in seconds. So now this means that if we come back here now, we can complete this and say our x is actually 0.02. 1 times 0.02 is still 0.02, and then we have a half times 0.02. Okay, so we need that calculator once again. So let's go grab it real quick. Where is it? There it is. I grabbed 2 of them. Okay, so we have 0.02 plus a half. I'm just gonna put 0.5 for a half times 0.02, and then our final answer is 3 over 0.03 as my final answer. Okay, so first of all, I need more space there. Okay, so my final answer is 0.03 seconds. Okay, the time t is 0.03 seconds. That's it. Hope you understood that. But in the event you didn't, you know what to do. Contact us for a session. And then it says here, the generator is now connected to an appliance with a resistance of 100 ohms. calculate the energy dissipated when the appliance is operating for 1 minute. 1 minute is 60 seconds. Okay, first of all, the first thing that you need to do here is grab the right formula. It's always about the formula. Once you have the right formula, you can just substitute according to what you've been given. So the right formula for this question here, let me write it down here. It is actually W is equals to, it should be in your formula sheet. Okay, so let me get from my formula sheet, V squared. But this V is not just any V, it's a RMS V. Okay, it's very important that you remember this. It's a RMS V. And then we have the change in time divided by R. Okay, let's check this out. Because it's an RMS V, it means that we need to start calculating the RMS V first. Okay, now if you go to your formula sheet and you check the formula for RMS V, you'll see that VRMS is actually equals to Vmax, the maximum V, all over square root of 2. Okay, so let's go read our maximum V. We can actually see from this graph our maximum V is 311. Okay, this is voltage, that's V. You can see it there, it's written V. Okay, so we can complete this. It's 311 divided by square root of 2. All right, we need our calculator again. There it is. Let's delete that one. We just need one of them. Okay, so we have, let me put that sign, 311, and then underneath we have the square root of 2. What do we get? We get 219.91. Okay, so we got 219.91 volts. What does that mean? That means now we can come back to our equation on top here and then put that 219.91, and then we're going to square it. The change in time is actually, as you saw, it's 1 minute, they told us here, which is 60 seconds. So we're gonna put 60 because we're dealing in seconds here. Okay, and then R, we've been given R as resistance is 100 ohms, so we'll put the 100 here. Now all that's left is for us to put this in a calculator. Let's grab our calculator down here, and then we're gonna say it's gonna be let me put this fraction sign, 219.91 squared times 60, and then at the bottom there I want 100. Cool. Wow, that's our answer, 29,016. Okay, so we've got 29,016, and let's make it joules. This answer is always in joules. Okay, so just remember energy. This is the energy equation. It's the work done. Work done is energy. All right, so that's it. That's it for this question 9. Thank you very much for tuning in. Good morning or evening, or maybe it's a good afternoon to you. I don't know, wherever you're watching. I hope you're having a good day. Well, welcome to MV Tutors. If you would like a tutorial session after this. Feel free to visit us on www.mvtutors.co.za, and we will be glad to help you. You can book a session over there on our website, or alternatively you can book one over right here by commenting under this video. Okay, so today we are doing question number 10. All right, so this is the last question of your 2021 June physical science paper 1. Okay, 2021. Okay, this you just wrote a few weeks ago, just a couple of weeks ago literally, and we're the first ones to take it out on a memo, on a video, so we're glad to help. All right, so let's get right into it. Question number 10. It says, well, when light of various frequencies is incident on the metal cathode of a photocell, photoelectrons are emitted from the surface of the cathode. The graph below shows the relationship between the maximum kinetic energy of an emitted photoelectron and the wavelength of the incident light. Okay, so let's see. The wavelength is on the x-axis, and then it looks like the kinetic energy is on the y-axis. Now it says, use your first question. Use the graph to determine the maximum kinetic energy of the emitted photoelectron when the wavelength of the incident light is 1. Okay, times 10 to the power -7. So what we want to do here is go to 1, or 1 is over there, and then if I draw that line there, it connects right there. Good. So what is that position there? So we have 10 here and we have 12. So between 10 and 12 in the middle somewhere, we're gonna have 11. Okay, and then it's gonna be 11.24, about 11.6, 11.8. Yeah, let me make it 11.8. Let's say it is 11.8. So you will write your answer as 11.8. Now you need to pay attention. Look at this. You need to multiply by that. 11.8 times 10 to the power -19 joules. All right. The next question says, what relationship between the maximum kinetic energy of the emitted photoelectron and the wavelength of the incident light can be deduced from the graph? Okay, now looking at the graph, I can see that the more I increase my wavelength, what's happening to my kinetic energy? It's decreasing. So that's the relationship we have here. So that's what we're going to write over here. Okay, which is gonna say exactly what we just said. As we decrease, no, it's not decrease. I don't want to decrease. I want to actually increase, because I want to start with the wavelength. As we increase the wavelength, the kinetic energy decreases, or the maximum kinetic energy decreases. That's it. That's all we're going to say about that. Then it says define the term work function in words. Okay, so if you remember this, you will know that work function actually is it's like the tipping point on top there before an electron, the amount of energy that's required before an electron is released. So let's say this work function work function is the minimum energy required or needed, let's say needed to use simple English, needed to release an electron. That's it. That's all. This is just theory work. Okay. Then it says use the graph to calculate the work function of the metal used as cathode of this photocell. Okay. So first of all, these questions, they're just about getting the right formula. Okay. So the formula that we need for this question, if you check it in your formula sheet, it's gonna be this formula. That's energy is equals to the work function plus the maximum kinetic energy. Okay, I'm just gonna put max like that. All right, so now we need to use this formula the way it's done. Now if you check your formula sheet again, E is actually H, okay, C divided by the wavelength, which is this sign lambda, okay, and that work function and that maximum energy, maximum kinetic energy. So what I want us to do now is actually start filling this in. Now if you check your formula sheet once again, the value of H, it's given, it's a given quantity, it's a constant, and it's always going to be, I have it right here, 6.63 times 10 to the power minus 34. Okay, and C is also a constant, and the value of C is 3 times 10 to the power 8. Now if you scroll down to your formula sheet, you will be able to see these values. And then we need to check what our lambda is from the graph. This we get it from the graph. Okay, so right, the one that we are actually interested is the maximum one. So if you can see, that's 4.5 and that's 5, so it's gonna be 4.5, 6, 7, 8, 9. So it's 4.9 times 10 to the power minus 7. That's our wavelength. It's 4.9 times 10 to the power minus 7. Okay, that's equal. We just filled this in. So now we come in to the other side of the equal sign, work function, which is what we're looking for. Now our maximum kinetic energy, we also get it from the graph. What's our maximum kinetic energy? Okay, so if you look at the graph, our maximum is actually, it comes to 0. Okay, so you can see at 4.9 wavelength, our maximum is 0. Okay, so that means here we'll just say plus 0. Okay, and then we can solve this. Now I'm going to need to grab my calculator. Okay, so let's grab the calculator right here. Okay, so we're going to put that, open the bracket, put it exactly as it is, 6.63 times 10 to the power, where's my power sign there, negative 34. And then we need to come down, close the bracket, open another one, and say 3 times 10 to the power 8, and then come down, close the bracket, come to the bottom, 4.9 times 10 to the power minus 7. There's an easier way of doing these times 10 just by using that function there. You need to say shift log and then, but I prefer the long way. Okay, so my final answer then is 4.0, let me make it 2 decimal, so 4.06 times 10 to the power 19. Okay, so let's write that down. So then we can conclude and say, therefore the work function after putting everything in a calculator is 4.06 times 10 to the power minus 19. And what is the unit? The unit is joules, just like that. Okay, so this is our final answer. That's our final answer. Okay, let's go read the last question. Last question says, calculate the maximum kinetic energy of the emitted photoelectron when the wavelength of the incident light is 0.5. Okay, so now we're calculating the maximum energy. We are going to use the very same formula. Okay, so this is 10.5. We're going to use the very same formula. It's not going to change. The only thing that's changing is what we're calculating. So we have E is equals to WO plus E. This is what they want, the max. Okay, so E, remember we have E is equals to HC and the wavelength. Okay, so we'll need, I'm just gonna put EK here, I'm not gonna put the max, but you should have it in the back of your head that it's that the formula includes max. If you are looking for the maximum, like here we use the maximum, but now we're not looking for the maximum kinetic energy, are we? No, we are not. We just want, well, actually we are the maximum kinetic energy at 0.5. okay, so what we're gonna do is that we're gonna start filling this in. H, we have H, remember we said it's a constant and it's 6.63 times 10 to the power minus 34. Close the bracket, open a new one. C is also a constant, it's 3 times 10 to the power 8. Okay, divided by lambda, which is the wavelength. Now the wavelength is the one that we are given. We are given the wavelength, it's 0.5. okay, times 10 to the power negative 7. So it's 0.5 times 10 to the power negative 7. It's gonna be equals to the work function. Work function doesn't change, it's always the same. It's the one that we just solved, and it's going to be 4.06 times 10 to the power negative 19. Okay, and then plus EK. Okay, it's EK max, it's maximum EK energy at this particular wavelength, so it still holds. Now we're gonna need to bring in a calculator. Okay, let's bring in the calculator, just like that. Cool. So now check this out. We're gonna open a bracket, 6.63 times 10 to the power, what's that, negative 34. Come down, close the bracket, open a new one, put the next constant, 3 times 10 to the power 8. Okay, come to the side, I'll close that. I'm gonna go downstairs now, and I'm gonna put 0.5 times 10 to the power negative 7. Okay, and then what I want to do is go to the side, because I want to take this 4.07 to the other side. So this is mathematical gymnastics, so if it comes to this side, I subtract it, so it's gonna be minus 4.06 times 10 to the power negative 19. That's it. What's that equals to? 3.57 times 10 to the power 18. That's our final answer. Okay, so then we can say, therefore, our maximum, now I have to put the max because it's at the end. Okay, it's the answer we're writing now. It was 3.57 times 10 to the power minus 18, and the unit is joules. Okay, ladies and gentlemen, lady or gentleman, whoever is watching, this is our final answer. Well, we've come to the end of this past paper. I hope you understood everything we tried to explain to you, but in the event that you didn't, you know what to do. Contact us through our website or through commenting under this video. Okay, thank you so much.